Is the voice okay?
Hi, Gila. Yeah, that's good. It's good.
Yeah, okay.
Perfect. You're okay.
So I'll stay.
Yeah, don't touch your your speaker or anything.
Yeah, okay.
Okay. Hi, Stephanie. It's good you're in.
Hi, Kitty. Nice to see you. Good morning.
Hi, Stephanie.
Hi, Gila. It's wonderful to hear your voice.
There will be like 5 minutes. The organizer will take 5 minutes to have like reports from different organizations and their land acknowledgement. Then he will hand it to me. I will have a really brief intro for the session, and then I'll introduce you, and then you can start. And then there will be a moderator for the Q&A, the 10 minutes Q&A for you. And then if you could join us at the very end for the panel, that would be great, just in case there are more questions for you.
Sure. And is it okay if I try sharing my screen for a moment?
Yeah, please try.
Think.
I'm going to add the co-host ability to make sure that.
Okay, thank you, Charles.
Yeah.
Oh, yes, thank you.
Okay, so you should have the ability to do it now.
Yep. Charles, could you also add me? Because I will be sharing my screen.
You're in, Kitty.
Yeah, thank you.
Guys, I'm going to be back in 1 moment. I updated my operating system and now it's telling me I have to restart Zoom in order to give it preference to share my screen. So I'll be back in a minute. And so this is why I was emailing you. I was a little nervous about testing things in advance. But
it's okay. We'll be here. Okay, I'll go get some coffee.
Kitty?
Yes. Yes.
Yeah. Hi, Charles.
Hello. Good morning.
Yeah.
What's up, Gila?
No, well, there was a slide saying field seminars.
Yeah, that's
that was me.
That's Charles.
That was you.
Yeah.
Okay.
Yeah.
So I'm just adding Jeremy in and Heather as well.
Okay.
A second. For some reason, the names are not ordered.
All right, I cannot. Hi, Jeremy. Welcome.
Hey, Kitty. How are you?
I'm good. Good morning.
How are things in Toronto?
Oh, Gila's here. Gila says hi.
Oh, hey, Gila.
Hi.
Yeah. How are things with you?
Good.
Hi, Paula.
Hi, Kitty. How are you?
Hi.
All well here. We have having 3 days of sunshine and summer, so I guess this is going to be it for this year. Next week is going to be cold again. Yes.
Yeah, we have this snow outside. I don't know if you can see it well outside my window, but there's actually snow just fell.
No snow in Toronto today.
Good.
Welcome back, Stephen. So we wanted to make sure everyone has their co-host access right now, just so that you're able to share screen and do all that stuff.
Yeah, Paula and Jeremy, Stephanie's back. And we're waiting for Heather. She will be here.
Okay. I know Heather's coming in, at least she's only going to be giving the talk in the afternoon, so I will keep an eye out for her.
Okay.
For any of the co-hosts, because we're giving the co-host access right now, if you have to leave for whatever reason and come back, just drop me a little message, and that'll be a reminder that you need that access, because sometimes we do have other people who will like allow you back into the room. So I just want to make sure you've got the access that you need.
Okay.
Hi, Athena. It's good to see you.
Hello. Nice to see you, Kitty. And nice to see you, Jeremy, as well.
Yeah. Hey, Stephanie. It's been a while.
Hi,
Nice
Jeremy. Yeah, it's great to see you again.
Yeah. Are you in Philadelphia now?
Not anymore. I was at Penn for the last 4 years, but I recently, in a mid-pandemic decision-making framework, decided to come back to Canada. So I took a job at Simon Fraser University in Vancouver, which I started in the fall.
I see. Okay.
Just keeping an eye on the time. It is 10:01, so we are scheduled to start in -1 minute. So I will be allowing the participants into the room.
And Charles, we will start at 10:05, right? You will start at 10:05.
Yeah, I'll hand it over.
Okay.
So just as folks are coming in, welcome to the April session of the MathEd Forum, where we'll be talking about the AI and automated reasoning in undergraduate mathematics education. It's a very specific topic today. We're hoping to learn a lot from the speakers who are joining together and from many of the participants who will be contributing, I'm sure, during the Q&A. So just before we get started, we would like to acknowledge the land on which the Fields Institute for Research in Mathematical Sciences resides is part of the treaty lands and territory of the Mississaugas of the Credit. We'd like to acknowledge and express gratitude to the Mississaugas of the Credit First Nation of the Anishinaabe peoples who continue to share their ancestral lands with us. Standard ground rules that we have for the session, just as a heads up, the sessions are recorded, so we do ask that everyone be aware of that. And just in general, we would ask that if you're not sharing, you may want to turn off the microphone to avoid some dog barking or anything like that, any kind of background noise. If you're not comfortable sharing, also your video, feel free to turn it off. And as always, we encourage everybody to participate in positive, collegial, and respectful discourse throughout the session. I'm just going to take a moment here to invite our members of the various organizations, the mathematics educational organizations here in Ontario, in Canada, and also internationally, to post in the chat any kinds of updates or reports that would be worth sharing with the forum today. Okay, so feel free to post that in the chat if there's anything you'd like to share. Thank you, Chantal. We have a talk coming up on March 31st, so just a few days. Math and coding. All right, so moving on to the agenda for today, and feel free to continue posting any kind of updates should you wish, but I'm going to hand it over to Kitty Yan, who's the co-organizer for this session, along with Gila, for just a brief overview of today's agenda.
Thank you, Charles. Good morning, everybody. Welcome to the March meeting of the MathEd Forum at the Fields Institute. Today, we invite you to the talks and discussions on the topic of AI and automated reasoning in undergraduate mathematics. The application of artificial intelligence to education has influenced the way teachers teach and the way students learn. One of the significant developments in mathematical practice is the ever-increasing acceptance of automated and interactive theorem provers. Despite the challenges, mathematics instructors worldwide have started to integrate them into teaching. In today's session, our invited speakers will discuss the contribution of AI to mathematics education and share their teaching experiences in using interactive theorem provers. Our first speaker is Dr. Stephanie Dick. She's an assistant professor in the School of Communication at Simon Fraser University. She's a historian of mathematics, computing, and AI in the post-war United States. She co-edited the book of Abstractions and Embodiments, New History of Computing and Society, forthcoming in 2022. She holds a PhD in History of Science from Harvard University. Without further ado, let's welcome Stephanie to kick off.
Thank you, Kitty. Hi, everyone. Can you see my slides okay? Wonderful. Yep. Great. Well, thank you so much to Kitty and to Gila for convening this meeting and for including me in the program. As Kitty mentioned, I'm a historian of science by training, and I am, I think, finally now, after many years of saying so, just about ready to send a book off to the press for review that documents the earliest decades of attempts to introduce computers to mathematical research and practice, the earliest decades of automated theorem proving and automated mathematical problem solving work in the United States. And it's on that research that I will draw today. The work that I do is not directly about how AI and automated reasoning were designed or actually used to teach students. Rather, my work is focused on different understandings and models of human intelligence, human knowledge, human reasoning that have shaped approaches to the automation of mathematics. However, models of the learning human mind and imagined students and imagined pedagogical practices shaped approaches to automation, even when they were not directly about teaching. Pedagogy and theories of pedagogy were sometimes the cultural and intellectual resources from which researchers drew when imagining how to design their automated systems, and imaginations of how future students might be taught what they might need to learn also shaped some of the early approaches to automation that I document in my work. So what I wanted to do with my time today is give an example of two different ways that pedagogy informed early automation in mathematics. An example both of how pedagogical considerations in mathematics influenced, I think rather famously, some early approaches to the automation of proof. And I'd also like to share an example of how the creation of an early repository of automated mathematical tools was seen as creating the possibility for very new ways to approach and to practice mathematics education. In particular, today I will talk a little bit about a program that many of you are likely familiar with. Maybe some of you have even heard me talk about it before, the logic theory machine, which was, of course, one of the first so-called artificial intelligence programs developed in the United States. It was an attempt to model and subsequently automate human problem solving in propositional logic that became paradigmatic for early artificial intelligence research more broadly. And I will talk about the Maxima system as well, which was among the first large-scale automated algebra systems meant to serve as a support for mathematical problem solvers across disciplines. In the case of the logic theory machine, the computer program was modeled in part on the works of a pedagogically minded mathematician at Stanford by the name of Polya, who many of you have likely heard of, who showed how theories, and this example shows how theories of the learning human mind informed early automation attempts in mathematics. In the case of Maxima, the designers of the system imagined that the practice of learning and doing mathematical problem solving would be radically transformed by the establishment of large centralized repositories of automated mathematical tools. And though their system was for the most part not actually used to teach and practice, it had built into it a new vision of what learning mathematics might even mean. So I'm going to introduce these two systems and these two different connections of early automation of mathematics to pedagogy as they played out in the very early history of automated mathematical problem solving. Starting with the logic theory machine. Its task, as again, many of you likely already know, was to automatedly provide proofs of logical theorems from a canonical early 20th century text in logic, the Principia Mathematica, which was written by two English mathematicians, Alfred North Whitehead and Bertrand Russell, around the turn of the 20th century. And in it is laid out a system of deductive logic, a set of axioms, a set of inference principles that Whitehead and Russell hoped or believed would be all that you needed in principle to do all of mathematics. Their hope, of course, was that the theorems from various branches of mathematics would ultimately be provable by deducing consequences from their premises using their inference principles. The computer program that was designed to do the very same was developed by these two men, Alan Newell and Herbert Simon. The two of them at the time were working at the Rand Corporation in Santa Monica, California, and were deeply invested in a branch of research there called systems engineering. In the wake of the Second World War, the Rand Corporation had been given the rather difficult task of modeling and predicting what future global wars were going to look like for the United States and to develop strategies for winning them. But this, of course, was a very difficult assignment, given that future global wars had so many unknowns. It was not known who these wars would be with, where they would be fought, what weapons and technological systems would be available and would shape the contours of strategy and the lived experience of warfaring. And systems engineering was one approach that was developed at RAND to try to make it possible to study future global wars without knowing any of those details. The idea was that rather than study war in any specific case, researchers at RAND wanted to study war in the abstract by identifying different systems that were involved in the waging of a war. They talked about everything as being like a system. A government was a system. The transportation infrastructure in a nation was a system. The weapons on an airplane was a system. And all these different systems could be modeled mathematically and treated in terms of the abstract relations between parts, the information that circulated within them, rather than all the details and specifics of actual countries, governments, infrastructure, and weaponry. And the reason that systems engineers became interested in logic problem solving was in part because both Newell and Simon, while working at RAND, came to believe that the modern digital computer and the human mind were also systems. Species of the same genus, in fact, as Herbert Simon put it, they were the same kind of system, one that took in symbolic information as input, processed it according to a set of rules, and in so doing, solve problems, output decisions, make judgments, and sort of perform other forms of intelligent behavior. For them, the human mind and the modern digital computer were both formal symbol manipulating systems. And so in principle, you could program a computer to perform the same feats as the human mind, the same way that the human mind did it, so long as you could identify what the rules for information processing were that the mind followed when it executed different types of problem solving, decision making, and judgment formulation. For them, the material substrata did not matter. It didn't matter if it was brains or computers or a mix of humans and machines. All that mattered for them and at the level of the system was the high level formal behavior in question, and in particular, the rules for symbol manipulation that they believed the mind executed when doing different types of intelligent behavior. And the logic theory machine was their first attempt to actually test this theory, to empirically develop a program that processed information in the same way the human minds do. But the first thing that Newell and Simon needed, if what they wanted was to automate human problem solving in logic, was a model or an account of what it is that humans do when they prove theorems, so that they might be able to implement that behavior on the computer. And this was where a mathematics education and a theory of mathematical pedagogy became deeply important for them. The model of human problem solving that Newell and Simon drew on when developing this program was inspired by the work of Hungarian mathematician George Polya, with whom Newell had studied closely as an undergraduate at Stanford University the decade prior. And Polya was best known for his contributions to mathematics education. In addition to being a research mathematician, Polya was deeply interested and concerned with mathematical pedagogy, as a number of European mathematicians who had come to the United States were at that time. And Polya believed, contrary to some of the idealizations and myths about mathematics, that mathematicians, of course, do not just deduce consequences from axioms in search of interesting true theorems. In his own classroom, Polya felt that that mythology about mathematical practice as a deductive practice fundamentally was misleading his students and failing to allow them to develop actual intuitive and effective mathematical problem-solving practices. He wanted to articulate and teach to students the real cognitive and paper-based practices that mathematicians engage in, which he thought went far beyond merely applying deduction rules and principles to axioms and known theorems. Mathematicians, according to Polya, do all kinds of other things. They start from something they want to prove and they work backwards looking for related problems. They experiment with cases, they look for analogies, they build models and counterexamples, they have all kinds of tricks. And Polya thought these tricks should be taught to the students of mathematics in order to make them better at actually doing mathematical problem solving. In 1954, he wrote, "Certainly let us learn proving, that is, let us learn how to deduce consequences from axioms, but also let us learn guessing." And crucially, Polya did not think that the strategies mathematicians use for actually doing mathematical work were somehow esoteric or tacit or inarticulable. He thought that many or even all of these tricks and practices could be made explicit. They could be identified and articulated by observing and reflecting on mathematical practice, and they could be formulated as rules to follow for problem solving. And these three works, of course, are the most famous places where he lays out his rules for solving mathematical problems in practice. And he called these rules rules of plausible inference, because while they do not always guarantee valid or true outcomes or even solutions at all, they did offer plausible paths and strategies for cutting through vast problem domains in search of an effective direction to take toward a solution. And he called these ways of guessing, these tricks and methods that mathematicians actually use in theorem proving, heuristics. He's the one who reintroduced this ancient Greek term to our conversations about mathematical problem solving. The Greek word heuristein comes from a root to find. It's a navigational term. And Polya imagined heuristics as navigational tools in a vast problem domain. How do you chart an effective path? How do you close down ineffective pathways that mere deduction might send you down in favor of strategies that are more likely to lead you to a solution to your problem? Alan Newell reportedly took every single class that Polya offered at Stanford, and reports having been very deeply influenced by these pedagogical accounts of mathematical problem solving. Polya's work on mathematical pedagogy offered exactly what Newell and Simon were looking for, namely a rule-bound model of actual human problem solving practice. And so they wanted to import Polya's notion of heuristics, and some of his heuristics in particular, into their work on automation in hopes of reproducing intelligent human behavior in the machine as they had desired. The logic theory machine operated according to two heuristics in particular. The first one was that it did not begin with the axioms of logic and then work forward by deduction, hoping to deduce theorems from Principia Mathematica. This, of course, would have led to an exponential explosion of data and was ruled out as a possibility for proof automation earlier in the 1950s. But instead, this program worked backwards. It started with a theorem from Principia that it wanted to prove, and then it would generate a set of so-called subproblems that, if they were true, would lead to that desired conclusion in a single permissible inference step. And then it would generate a set of subproblems for those subproblems, and so on, in the hopes that eventually the axioms themselves would be generated as subproblems. There was no guarantee that this would happen, but if it did, you could then run that tree search in the opposite direction and have a deductive proof of the theorem in question. And Newell and Simon acknowledged that this was only a first step in modeling the complex ways that humans prove theorems, but they thought it was a good start, and that this was proof of concept, that the way human beings learn and practice and solve problems in mathematics could be modeled as rule-bound operations and translated into computer programs. The logic theory machine was the only running computer program that was presented at the infamous Dartmouth Conference of 1956, and it had a huge impact on the early field of artificial intelligence. And especially it was this heuristic approach that was taken up by later AI practitioners well into the 1980s. It was also only a very superficial relationship to the heuristics of Polya. Alan Newell wrote an essay later that, in spite of the fact that so many people working in early AI were excited about the idea of heuristic as a means of translating human practice into computer programs, they mostly did so in very superficial ways. The heuristics that Polya documents in his pedagogical texts are rich and complex. The heuristics that were implemented in early AI tended, like these two, to be very basic and rudimentary and not capturing the same complexities that human practice consistently demonstrated in different fields. But nonetheless, early AI practitioners adopted this heuristic approach, wanting to do the same for medical diagnosis, for writing, translation, or interpretation, and for many other fields, as Newell and Simon had done for logic, namely identify what heuristics are at work in expert human practice, translating them into a set of rules, and then automating them in hopes of reproducing that behavior. And in case you're interested, I have an article from a while back about the logic theory machine in which I document how inhuman this model of problem solving actually becomes when it is implemented, when you can't ignore the material reality of the computer and treat it only in the abstract. When Newell and Simon had to meet the affordances of this machine and its material specificity, their human model became rather inhuman indeed, but I don't have time to get into that today. I just wanted to highlight how a theory of learning and teaching mathematics was deeply influential for how early AI took shape as the identification of rule-bound heuristics as Polya imagined them. So many of the followers of Newell and Simon in early AI took up their interest in heuristics, as I said, aiming to identify those modes of actual practice in different domains and translate them into automatable models. This represented an attempt to automate human reasoning and a belief that reasoning was the chief cognitive faculty responsible for human intelligence and capacity in mathematics. That if you wanted to reproduce intelligence in a machine, your job would be to understand what reasoning is and how it is operationalized in the human mind, and to automate that model in your machine. Herbert Galanter, who is another automated theorem proving researcher very early on in the 1950s, created a theorem prover shortly after the logic theory machine for geometry, where he expressly wanted to create a program that would perform well on the famous Brooklyn Tech high school exams that he and many of the other early AI researchers in the US Northeast had taken. Many practitioners went through that high school and their math exams were notoriously difficult. And so even while people were attempting to automate heuristics built on theories of mathematical pedagogy, they were also testing and benchmarking the capacities of their machine against some of the same tests, exams, and benchmarks that we use to assess student learners. This was a theory of human reasoning as symbolic information processing and of mathematical problem solving as the application of formal heuristics. Here we see that mathematics pedagogy was used as a resource for modeling the learning human mind and human intelligence in general in order to make it more possible to automate. But of course, I imagine that many of you in this room do not need me to tell you that this approach to artificial intelligence, human-inspired, heuristic, rule-bound modeling of problem solving in different domains, did not win out and in fact failed rather miserably to return on the promises made about what would be possible with this approach to automation. It also did not win out in the automation of mathematical theorem proving. Far more sophisticated systems based on more powerful logics like the resolution principle and its many variations took over within the field of automated reasoning that for the most part actually split from artificial intelligence at this time because AI remained interested in reproducing human intelligence, whereas the field of automated reasoning became interested in turning toward the question of what computers might be able to do with powerful logical formalism that may escape the limitations or historical contours of human approaches to working within the same. But the second example of how pedagogy was a present concern for early automation of mathematics that I want to share does not actually come from the field of automated reasoning, but rather from an alternative approach to early artificial intelligence that was developed in the 1960s and 70s called expert systems. Researchers in this area believed that Newell and Simon and other early AI practitioners had gotten something deeply wrong about human intelligence. namely that human intelligence is not a product of our reasoning faculty alone, or even our reasoning faculty primarily, but rather that human intelligence was contingent on knowledge. Our ability to exhibit intelligent behavior in different disciplines and fields and domains is contingent on what we know about those domains, and not our ability to right reason or to think correctly about problem solving in a general way. So developing automated systems based on the automation of reasoning, expert systems researchers believed, would only ever reproduce a small, finite, and fixed subset of human intelligence. What would be required for more powerful artificial intelligences would be to elicit and encode for automation what humans know, to create vast databases of human knowledge, often represented as if-then rules that a computer could follow in order to recreate, in a sense, the knowledge that humans bring to different domains of problem solving. In response to the mounting evidence that the prior approach of heuristic reasoning, human-inspired based automation, one of the founders of expert systems at Stanford, Edward Feigenbaum, wrote, quote, "We must hypothesize from our experience to date that the problem-solving power exhibited in an intelligent agent's performance is primarily a consequence of the specialist's knowledge employed by the agent, and only very secondarily related to the generality and power of the inference method employed. Our agents must be knowledge-rich, even if they are methods poor." Like Polya, Feigenbaum rejected the idea that expert knowledge was something tacit, esoteric, hidden, inarticulable, and proposed actually that everything that human experts know could, at least in principle, be elicited and made explicit and formulated as a set of rules. The job of doing this work, of actually talking to experts and trying to find out what they know in order to encode it for automation, was the work of the so-called knowledge engineer who engaged in so-called knowledge acquisition. And Feigenbaum was confident that a good enough knowledge engineer would be able to elicit from an expert knowledge that they themselves would be unable to articulate. Much of this knowledge, he wrote, is private to the expert, not because he is unwilling to share publicly how he performs, but because he is unable. He knows more than he is aware of knowing, but we have learned also that this private knowledge can be uncovered by the careful, painstaking analysis of a second party. So the goal of expert systems engineers was to elicit from human experts what they know and translate that into rule-bound operations that could instead be automated. One of the earliest expert systems, although it was only called this retroactively, was the Maxima system developed at MIT beginning in the mid-1960s. It was Maxima for the Project Mac symbolic manipulator, and it was among the first large-scale, nationally distributed on the ARPANET, so-called algebraic or symbolic systems for solving problems in mathematics. It was designed to assist in mathematical problem solving by offering ready-made libraries of automated tools, functions, and procedures that were supposed to help mathematicians, engineers, and other mathematical scientists and technical practitioners in solving their problems. The system had modules for integration, simplification, it could factor expressions, it could multiply matrices, it could do a lot of things that technical practitioners earlier had to do sometimes rather tediously on paper. The emphasis in the Maxima system was on non-numeric or symbolic or algebraic operations rather than on arithmetic operations and complex calculations that computers had more commonly been used for in mathematical problem solving up to this point. By the 1990s, Maxima had largely been displaced by more powerful and user-friendly systems that I'm sure many of you are familiar with, like Wolfram's Mathematica and Maple and so on. But in an open source form, it's actually still in use today. So I came to Maxima with an interest, of course, in wondering what it actually looks like to create an automated repository of mathematical knowledge. And here again, we actually see the imagination of the learning student come onto the scene. In trying to describe the system and how they had conceptualized it, Joel Moses and other core developers wrote, quote, Our rough hypothesis is that a mathematician knows perhaps 10,000 mathematical facts. For example, if a student learned 4 facts an hour, 4 hours a day, 5 days a week, 9 months a year, for 4 years, he would learn some 12,000 mathematical facts. The average mathematician may not be able to sustain this pace with complete retention, but he has been learning for a longer time period. A very romantic picture, of course, of learning mathematics as a student. The goal of the Maximus system was to become a repository of the tens of thousands of mathematical facts that not just an individual student might know, but that the mathematical community as a whole might know. This was meant to be an externalized mathematical memory, modular, communal, and rather gigantic. It would have what an individual learns, but also what a community knows over centuries, making possible, they hoped, the recognition of vastly new patterns and problems, the accumulation of more and more interesting knowledge as people could turn their attention away somewhat from learning and developing facility with what we already know how to do in order to open up space, time, energy, and creativity and support for finding new things that we don't already know how to do. The belief was that the consolidation of mathematical knowledge makes mathematical facts more useful. And it also shifts what it is that mathematical problem solvers are required to know. Maxima developers were excited about the prospect that users need only know when to use a certain mathematical operation. They need not know how to actually execute it themselves. Problem solving with Maxima, I have argued in some of my published work on this theme, became the art of taking a problem and finding a way to solve it by charting a path through the available operations of Maxima. Problem solving actually meant planning a path through Maxima's capabilities that could lead to a solution to your problem. So as the problem solver, your job was to say, okay, I think first to solve this problem, I need to factor these expressions. I need to simplify them to remove these variables. Then I need to do this, and then I need to do this. And charting a path to a solution that moved through the different operations Maxima had on offer became a mode of problem solving. And it shifted the user's knowledge away from problem solving itself and toward the Maxima system, its capabilities, its nuances, its idiosyncrasies, its obtuseness, its underlying structures, and its capabilities and limitations. Moses and the other developers of the Maxima system believed that if a system like this could be developed comprehensively, it would transform a lot, not just about how mathematics was done, but also how it was taught. There was no one set of rules that controlled the entire system, nor was there any one standardized formal logic that was required to operate within all of the different modules. Instead, the idea was that each module could stand alone. It could operate according to its own internal logic. Its only job, each module, was to perform a certain mathematical operation that a mathematician knows how to do. The modules could be picked up independently of one another and used in various ways, used in different orders. And the different sequences of modules became something that users of the Maxima system came to know very well. Each module was meant to encode some part of mathematical knowledge. So there's a module for factoring. There were several different modules for doing algebraic simplification according to different understandings of what it means to simplify an algebraic expression. There were modules for matrix multiplication, modules for differentiation and integration, and so on. And the idea behind Maxima, their theory of knowledge, was that it was fundamentally procedural. That for the most part, what mathematicians know is how to knowledge. They know how to integrate. They know how to simplify. And that this procedural character is what allowed mathematical knowledge to translate into automation. Michael Genezareth, who was an early developer and user and did a lot of work on troubleshooting and helping struggling users make sense of the Maxima system, he wrote that it was a conception of mathematical knowledge as a body of programming rules. They had to be procedural. And this led to a lot of problems because I'm sure, as many of you know, mathematicians are used to working with certain kinds of definitions or ideas or constructions that do not easily translate into programming rules and that may not be procedural in the way that mathematicians work with them. This is a really simple example, just to give you a sense. We could define even numbers in this way. N is even if and only if there exists a number m such that n is equal to 2m. This is a perfectly good definition of evenness, but it doesn't give an explicit procedure. We could easily extrapolate one, but it doesn't give a procedure for creating even numbers or even for checking if a given number is even. So this kind of definition could not be given to the Maxima system. It had to be made procedural. So a procedural definition of evenness might be divide n by 2. If there is no remainder, then n is even. Maxima required, for the most part, that definitions and anything else mathematicians know be given a procedural formulation in this way. But of course, not all mathematical definitions could be made procedural in this way, and Genezareth identified some of those areas, but it was also counterintuitive and difficult to define certain mathematical concepts in this way. And Genezareth identified this as one of the main reasons that Maxima was notoriously difficult to use in the beginning, was that it required mathematicians to learn to think differently about their objects and about problem solving in general. They had to learn to think more like programmers. Namely, they became planners who found procedural definitions for the things they wanted to work with, and they were planners in the sense of charting a path through the modules of Maxima and calling it problem solving. So the Maxima system was meant to be a repository of mathematical knowledge understood as modular and procedural and discrete. It would have a module that was meant to reproduce all of the things that mathematicians know how to do as an automated process. And the belief was that this would be deeply liberating, that people would spend a lot less time doing really tedious problem solving themselves and would only need to know when certain operations were needed for a problem solution, not necessarily actually having to build one. And this is one of the things that has interested me most about the automation of mathematics, and it relates directly to the question of pedagogy. With the introduction of automated tools, we see a shift in which students are imagined to learn about the system, its systems of representation, its possible operations, its modules, its structure, as much or sometimes more than learning about the underlying mathematics. And I've written and published work about Maxima and other related systems that you can demonstrably see users' focus and intuitions and understanding shifting towards an understanding of the system itself, its nuances, idiosyncrasies, its capabilities, how it behaves with different types of inputs, with different sequences of modules, and mathematical problem solving becomes intimately related to this empirical knowledge of how the system works. And in some cases, this does shift away from an understanding of or even interest in the underlying mathematics themselves. Solving a problem becomes charting a path through the capabilities of the system rather than solving the problem directly yourself or even necessarily knowing how to do so. But this was the feature, not the bug, of course. Maxima developers were very excited about this and believed that Maxima would ultimately replace more traditional mathematical education. Writing about textbooks and mathematical texts, they wrote, quote, "Books would still be used," that's in mathematics education, "but only for tutorial exposition," by which they meant tutorial exposition for how to use Maxima. So the books would support your understanding of the system, but they would not be needed to teach people other things because Maxima would teach them what they needed to know about mathematical problem solving. And to finish up this talk, I wanted to share one story about this. Of course, this vision did not come to fruition. There's a really notable trend in the history of automated theorem proving and attempts to produce centralized automated mathematical databases, where the idea is that after centuries of trying, we may now actually finally be in a position to produce a centralized, standardized, formalized, automated database of mathematical knowledge. They couldn't do it in the 19th century when they tried to do it in books. They couldn't do it in the 20th century when they tried to do it with the logical formalisms and computers they had available. But now we'll be able to do it. It's always seen as this, just around the next corner, we might have the tools to achieve this vision of a consolidated, centralized repository of mathematics. But I'm actually not holding my breath, and I love the chase of it, that this is something that mathematicians are constantly pursuing, but somehow never arriving at the type of full comprehensive centralization and standardization that is a dream for so many. But when I did a series of interviews with Maxima developers, I asked them about this pedagogical question. Did this system change how they or their students learned mathematics or what they learned? And the most interesting answers to that question emerged around the subject of symbolic integration. Several of the early users of Maxima reported to me that the fact that Maxima could do symbolic integration seemed like magic to them, because at the time in the 50s and 60s, calculus textbooks still presented it as an art form, only learnable through much practice and the cultivation of deep intuition and understanding. That symbolic integration would be too cumbersome to do in terms of elementary operations for a person, and therefore it required heuristics, ingenuity, a kind of craft. So the fact that Maxima could do it struck some as surprising. Mathematician Jeremy Teitelbaum told me, quote, "One of the things that Maxima did that seemed like science fiction to me at the time was symbolic integration. I think in some ways that was the showpiece skill, because I think people got that you could do algebra and stuff like that, but the fact that you could do symbolic integration, that was really amazing." And he went on to tell me that this led to some interesting debates or conversations around how or if or how much to teach students about symbolic integration. And it's something I would actually love to hear people in this room speak about today, because from these interviews, it sounded to me like an ongoing conversation, but I haven't kept up to date with it at all. We know from history that once something becomes trivially automated, like long division, we sometimes stop teaching students how to do it. But in the case of symbolic integration, it seems to have created an interesting discussion around what the point of learning mathematics is. Teitelbaum went on to say, "I've had conversations with people like, I don't understand why we're still teaching people methods of integration, because it's now been almost 50 years since this problem has been completely solved on the computer. The way humans are taught to do it is by heuristics. There's not an algorithm. It was possible to do it in terms of elementary functions, but they aren't practical for humans to use. So we teach people very inferior ad hoc methods to solve these problems when there is a very good analytic solution, easily executable in most cases by computer." Teitelbaum indicated that it's an ongoing question, at least in his community, about how much of the heuristic art of symbolic integration is worth teaching mathematics students today, given the automated tools that are available. Some have held on to the idea that learning to do it the human way as an art is a way of teaching students a way of thinking and being that is valuable for the work of mathematics, whether it's actually needed to solve these problems or not. Others seem to think students should be taught these methods only a bit until they have some understanding of integration, but then they need not practice extensively in order to develop deep intuitions or sensibilities about this. And I was so fascinated by this conversation because it is very familiar to a historian. In fact, it is an almost identical conversation to a debate that unfolded in 19th century Europe between the advocates for algebra, which was relatively newly on the scene, as shown as a way of allowing geometric problems to be solved by more mechanical means, as opposed to needing decades of training in how to do ruler and compass Euclidean constructions, for which famously, even after 2000 years, there was never any established algorithm for how to go about doing a Euclidean construction, or even knowing what was the appropriate construction to do to solve different kinds of mathematical problems. And this debate has been the subject for some of study for some of the best historians of mathematics in the business. Here's a slide with some of their work in case you're interested in following up on this. But they discovered that in the 19th century, those who defended Euclidean constructions did so because they thought that learning how to do them cultivated a certain way of being a mathematician. Spatial intuition, a deep understanding of figures and constructions, they describe an inner world of the geometer, capable of knowing how to do a certain type of construction, how to go forward with figures and lines. And it had actually deep religious significance and ethical significance. They believed that learning to do this craft was learning to be a certain kind of person with a certain kind of inner world and cognitive landscape. And they feared that algebra and the mechanization and dephysicalization of geometric problem solving would forfeit what they thought was an essential part of mathematics. Algebraicists, on the other hand, saw no drawback at all. Algebra spared us from the decades required to learn to have to do these Euclidean constructions. It spared us the decades required to cultivate the art and intuition to do it well. They saw this as a democratizing effect. It made mathematical problem solving more generalizable, easier, more accurate, more efficient, more accessible, and more practical for the solving of geometric problems. And this debate went back and forth for almost a century, and we no longer learn Euclidean constructions for the most part, but I think that this same debate about what the point of learning mathematics is still with us today. And my guess, though you will be the ones who know this, not me, is that our automated tools for teaching and doing mathematics have raised similar questions that cut to the heart of what it means to learn mathematics at all. Is that a project of knowing how to solve problems, or is it about becoming a certain type of thinker or knower in person? And if so, what is the character of that person? The outsourcing of knowledge and practice might seem like a threat to some part of what mathematics is understood to do, but everything hinges on what kind of automated tools are being designed and how the division of labor between the learner or problem solver and the machine is worked out. And I will stop there. Thank you so much for your time, and I hope that was of interest for this community.
Thank you so much. That was absolutely wonderful. I have 100 tabs open, and I look forward to your forthcoming book about this. This is amazing. We have a very small amount of time for questions. People at Forum tend to like asking questions, so I think we can take one as Jeremy gets set up for his talk. You've been unmuted, so please, if you'd like to speak up, go ahead. I'll voice Lee's question in the chat. My question is how reasoning and knowledge are defined and translated to computers. Can computers really understand human knowledge?
Great question, Lily. And if you figure out the answer, please let me know. The one thing I can say for certain about this question, which is deep and at the heart of all of the research that I do, is that I think that a lot of what happens in automated reasoning and artificial intelligence are better understood as redefining what knowledge and reasoning are, rather than describing what human knowledge and reasoning are in practice. I think there's a long history in analytic philosophy and mathematical logic of presenting these formal models of reasoning or knowledge as descriptive, that they are describing what the mind does, that they are making explicit how the mind works. But there are a lot of reasons to think that actually a lot of logic and analytic philosophy are rather normative systems. This is how we should reason. This is how we should think. This is how we should train and discipline reasoning agents, whether it's the mind or the machine, in order to not err or produce contradictions or run into mistakes. But especially in the context of expert systems, it always looks to me, of course, like what happens is that anything that can't be defined procedurally, anything that can't be formulated as an if-then rule or given a procedural formulation, just gets left out of what we mean by knowledge. So knowledge keeps getting redefined in a way that excludes what cannot be represented in whatever formalism we're currently using to say what knowledge is. So I think there's a kind of moving target where these terms get defined in new ways when sometimes those definitions are called descriptions, and that there's also this way that things keep getting defined out of mathematics if they can't be translated into the formal tools that mathematicians are currently using? So that's what I would say, but it's obviously the biggest question in the business, and I don't have an answer to it.
Fantastic. Thank you so much for that talk. That was really wonderful. So if the audience could think in the chat, that's wonderful. Our next talk is Jeremy Avigad of Carnegie Mellon University. He's the director of the Hoskinson Center for Formal Mathematics, and his interests are in mathematical logic, formal verification, and the history and philosophy of mathematics. Today, Dr. Avigad will be telling us about formal assistance and mathematics education.
Okay, can everybody hear me okay and see the slides?
Yes.
So I'm not, yeah, okay, good. Okay, yeah, so thank you for having me. I'm delighted to be here. And Stephanie, thank you for a wonderful talk that sets a lot of good context for the things I'd like to discuss here. So let me start by saying a few words about formalization of mathematics in general. Since the early 20th century, we've understood that, at least in principle, ordinary mathematics is formalizable. That is, you can represent mathematical statements and proofs in formal axiomatic systems with very precise grammars and rules of inference. What's changed in the last few decades is that now, to some extent, it's possible to formalize mathematics in practice. So there are these computational proof assistant tools, and working interactively with such a tool, users can construct a formal axiomatic proof. So you work with the computer to construct a formal argument of a mathematical theorem. And these things are often called proof assistants. I like to think of them more broadly as digital mathematical assistants. It's a technology that lets us represent our mathematics in a digital format. So it lets us represent definitions, statements, and proofs. And once you've done that, you have them in a format where you have complete detail, and there's a very precise semantics. And the system comes with the rules that tells you, how you're allowed to construct statements and how you're allowed to reason about them. So you can think of this as, as being kind of an extreme endpoint in the goal of, having mathematics being rigorous and precise, in the sense that it's gotten so rigorous and precise that you can even, represent it in a form that the statements and claims can be checked by computer. So in this talk, the title is almost misleading or bait and switch. I said it's about formal assistance in mathematics education. I'm going to focus on one particular proof assistant called Lean, which is one that I've been working with for a number of years and know well. So I want to emphasize that there are a number of proof assistants out there. So the focus on Lean is not a value judgment or anything like that. And what I want to do is, if I may, I'd like to start by just giving you a demo of what it is like to work with Lean. So let's see. So right now, you're looking at a Lean running in VS Code. Let me make the font bigger. Hopefully that's readable. And so, okay, so let me emphasize that if you've never seen this sort of thing before, I don't expect you to fully understand what's going on. I just want to give you an impressionistic picture of what it means to work with a proof assistant. And I also want to emphasize that right now, I'm not talking about teaching or anything like that. I just want to sort of get on the table what it means to work with a proof assistant so that we have, that'll support the discussion later on. But okay, so working in an editor, Lean is running in the background. I've imported some things that I know I'm going to need. And what you're looking at is a definition of the factorial function from the natural numbers to the natural numbers. And it's a recursive definition. So this means that factorial of 0 is defined to be 1. And then factorial of n plus 1 is defined recursively to be n plus 1 times the factorial of n. Okay, and having defined, I should mention that there is a computational interpretation to Lean. So, at this point we can, evaluate some factorial. So if you look at the window here, you'll see there's 10 factorial, and you can see, 100 factorial or even 1,000 factorial. I don't know if there's a way to get, it scrolls off the screen. So you can compute. But again, to mathematicians, that's kind of almost irrelevant. What we really care about is proving things. So here's a statement about the factorial. So one feature of the factorial of n factorial is that all the numbers from 1 to n divide it. And so it's tempting to say that everything less than or equal to n divides it. But then you have the trouble that you have to exclude 0. And it turns out that in the formal world, a convenient way to do it is rather rather than just say everything not equal to 0, you start with sort of with a +1. So this is the statement that for every I less than n, I plus 1 divides n factorial. So in stating the theorem, now Lean is expecting me to prove it. Okay, and here, let me get rid of some of that clutter. So I've said that I would prove it, so there's my goal. I'm supposed to prove that statement. So if for an arbitrary I, let me introduce the number I and the hypothesis. So, oh, I'm sorry. Let's prove this by induction. Okay, so this is natural to prove by induction. So I'm going to say induction on n, and I'm going to name the variables in the inductive step. Okay, so there's a base case. So there's the 0 case. I have to show that everything less than 0. It's true for everything less than 0. And then it's true for everything up to n plus 1, assuming that it's true up to n. So the base case is trivial because there's nothing less than 0. Right. So, you know, the hypothesis that there's something less than 0 is just contradictory. And I happen to know that there is a bit of automation in Lean that just knows that that's a contradiction and will get rid of it for me. But now in the inductive step, so let's look at what we have. We are trying to show that, so we assume the inductive hypothesis that everything less than n divides n factorial. This n dot suck is, unfortunately, it's another notation in Lean for n plus 1. So we need to, so for now we have an arbitrary I. We're assuming that I is less than n plus 1. And we want to show that I plus 1 divides the factorial of n plus 1. And so what we want to do here is now do a proof by cases. If I is less than n, we're going to be able to use the inductive hypothesis. And then in the other case, I is equal to n. So to split on cases, there's a little bit of trickery here. So I want to use the fact, I mean, maybe some of the Lean experts in the audience will tell me that there's a better way to do this. But the way I figured out to do this while working it out last night preparing this talk is this, let's see, H2, is to say, so since I is less than n plus 1, it's less than or equal to n, which means that it's either less than or equal to n. And so if you look at what happened after this magical line, I have kind of two cases, one where I is less than n, and one where I is equal to n. And there's a further trick that I can do. So in the case when I is equal to n, we just want to substitute, we want to carry out that substitution. So there's another tactic called R cases, and it will let me do this. And so this was just a little bit of shorthand where in the inductive step, I just did the substitution right away. Okay, so where are we? So I'm trying to show that I plus 1 divides n plus 1 factorial. Okay, but we know that I divides n. Okay, so we want to use the inductive hypothesis. So first of all, let me expand the definition of factorial. So n plus 1 factorial is n plus 1 times the factorial of n. So let me do that by saying rewrite factorial. Okay. So now I see that it suffices to show that I plus 1 divides the product. And for that, I want to use the fact that I plus 1 actually divides n factorial. Right? So I can do that by applying a rule that says to show that you divide the product, it's enough to divide the right-hand side. Okay, so let me say apply, divide, mul, divide right. Okay, so I've told Lee that I wanted to prove that by proving the right side. And now I can use the inductive hypothesis. So I can say apply the inductive hypothesis at I with hypothesis I less than, and that took care of that goal. And finally, the left side is easier. Again, well, let me kind of rewrite factorial. But here it's easy because I plus 1 divides I plus 1 itself, and therefore it divides the product. And so I think I divide mul. I think that worked. Yep, and that's a theorem. Okay, if that went by quickly, don't worry about it. That's just kind of an impressionistic picture of what interactive theorem proving is. And so, it's a technology that lets us do mathematics in a digital way. And it's led to some excitement in recent years, that now we have a technology that can help us reason better and precisely and catch mistakes, right? So the computer is checking everything we type and every rule of inference and sanctioning it as correct by the standards of the axiomatic framework. But it also gives us ways of building mathematical libraries. So you can collect pools of theorems that have been proved this way and build them into these grand libraries. And these are repositories of definitions and theorems and proofs. People collaborate to build them. So the Lean Mathematical Library has about 800,000 lines of code. I know tens of thousands of theorems in it. Once you've got your mathematics in digital form, you can use it as a front end to computer algebra systems, numeric computation. You can use it as a basis for using automated reasoning, machine learning, and finally, teaching mathematics. So let me focus on this last aspect. So when it comes to using formal methods in teaching, there's some negatives, and from the demo, I mean, you get a sense of all the things that are bad about it. I mean, to use a proof of system, you really need to know what you're doing. You need to have a lot in mind. I mean, I kept typing all the names of these commands and the names of the theorems. There's a lot that you have to keep in your head. The syntax is unforgiving. If you put commas in the wrong places and so on, you get these error messages that are cryptic and not helpful. And it can be really frustrating. Even doing simple things can be very difficult with a proof assistant, and that can be demoralizing. And I've been doing this for more than 20 years now. I've been working with proof assistants, and still, there are times when I just feel like an idiot. So it can be really demoralizing. And if you're like me, when I teach students, I want them to be happy. I want to give them, tasks and homework assignments where they can feel good. And so, it's hard to give them something like that where it's just kind of, you're just constantly beaten down. Right. But the thing about proof assistance is that, if the lows are low, the highs are pretty high, right? So there's a lot of good things you can say about it. So first of all, throughout the ages, people have dreamed about having symbolic languages that are powerful enough to represent all rational thoughts and, in which anything you can express and anything that you can prove. And now we have one, right? We have a very expressive mathematical system. And, there's something exhilarating about that. It's a lot of fun to play with. For teaching, I think the main thing is that feedback is instantaneous. So while you're working with a proof assistant, it's interactive. The system is constantly giving you feedback, letting you know what's right and what's wrong, right? So when you do something right, you know it right away. And when you do something wrong, you know it right away. So it's not like giving students homework, they write something down, they don't know if it's right, they send it to the grader, comes back a week later and it's all marked up, and by that time they don't even care anymore, right? It's just you against the machine, and and when you're right, you know it. And for that reason, it can be a lot of fun. And so I think the task with using such tools in teaching is to accentuate the positive and maximize the pros and minimize the cons, right? So when you give students assignments, you have to choose the tasks very carefully. You have to make sure that they have the information really right in front of them that they'll need to carry out the task. And then, we can try to be clever and provide better interfaces and better automation that hides some of the complexity. So they need to, remember that much extraneous detail. Right, but so it's kind of a game of trying to make the tools as usable as possible to support the educational practice. Okay. And so, here's some questions for, educational researchers, now that I have you here. So, people often compare using a proof assistant to like playing a video game. I mean, there's this constant challenge of you're trying to do something, you're frustrated, then you get it, and then it feels really good. And then you have the next one, it's like getting to the next level, the tasks become harder, but you get better at it, and so on. And, anybody who's worked in the field can tell you that there are times when you're just kind of absorbed in what you're doing. And the hours can just melt away. I mean, you find that just hours later, you've been totally absorbed, engrossed in what you're doing, and you can just get really sucked into it, right? So one question is this for everyone? I mean, so I can tell you that mathematics and computer science majors at top universities, computer nerds, people like me who are kind of invested in the technology. I mean, we can get sucked in like that. So one question is, is this really good for math education more broadly, or is it really, really kind of a narrow focused audience? And then another thing that I think we should be thinking about very seriously is, so I mean, the first question is, can we get, lots of people to play this computer game? But, the other important question is, do we want to? And this really touches on a lot of themes and questions that Stephanie raised. I mean, if your goal is to teach people to use a proof assistant, then okay, teaching them to use a proof assistant is a good thing to do. If your goal is to teach mathematics, teach students to think and reason mathematically, the question is, does it help? And I can tell you that, this is a good topic for discussion. I can tell you that people in the field feel that it certainly does. I mean, you really have to understand the mathematics to be able to formalize it. And while you're working with it formally, you find that things you thought you understood were not as simple as you thought they were, right? So there's kind of a clarification. And, you find yourself restructuring and reorganizing knowledge in a way that helps you understand it better. But again, that's something that, with educational research, we should be able to quantify that a little bit more. I mean, is this just kind of a high stakes game? You have to be once you learn mathematics, then you get to play the video game, or does the video game really help you learn mathematics? And yet another question that I'd like to raise for educational researchers is, I've come across two attitudes towards teaching students to reason mathematically and write mathematical proofs, right? So one attitude is that if you want to do that, then getting students to reflect on, on logic and the structure of a proof is really essential, right? You have to get students to realize, when you're assuming, proving if A, then B, you assume A, and then you're trying to prove B. Students have to keep track of what hypotheses are at play at any point in the proof. They have to know, proof by contradiction, proof by cases, what a universal statement is, what an existential statement, what the different patterns of reasoning are, right? And so, doing that formally or doing that with some symbolic notation is helping them understand, how to write an informal mathematical proof. And the other attitude is that simply is nonsense, right? Logic is trivial, right? Just, students are smart. Just teach them the mathematics, right? They can tell, if you just do it, if you don't have to, if you just do proof by cases, you don't have to give it a name. You don't have to have all kinds of fanfare. Just, do proof by cases, and they'll learn how to do it. And I know excellent educators who on both sides of the divide. People who I mean, students love them. Students go on to do great things. So yeah, it's probably some kind of combination of both. But this is one axis I've kind of observed when it comes to teaching mathematics. Okay, so yeah, so when you use interactive theorem proving with teaching, look, you might be using it to teach mathematics. You might be using it to teach computer science. You might be using it to teach logic. Your goal might be primarily to teach the mathematics or the computer science or logic, or specifically you might be interested in teaching formalized mathematics or how to use formal tools in computer science or how to use formal tools in logic, right? So depending on your goals, that will affect what you teach and how to teach. We might be interested in teaching, elementary school students, high school students, college students to research mathematicians and computer scientists. And so, when you talk about teaching with interactive theorem proof, I mean, it's a really wide landscape, and depending on what you want to do, different things might be appropriate. Also, of course, teaching mathematics can mean, teaching mathematical calculation and computation. So, like, an introductory calculus class is mostly, calculation and computation. But so here for this talk, I'm really thinking more about mathematical reasoning and argumentation. So teaching students how to construct mathematical arguments. Okay, so yeah, so people are doing it. So by the way, I should have mentioned that these slides are already on my webpage, and these are clickable links, so you can find the list later. But I already know of a number of people who are using Lean to teach mathematics. So Kevin Buzzard in London, Heather we'll hear about, we'll hear from soon, Gihan Marasinghe, Patrick Massot. Sina Hasratpour is a postdoc with Emily Reel at Johns Hopkins. So Emily has used Lean in the past. Now Sina is Matthew Ballard, and Gila, reminded me of a few others. So a number of people are using it. So there's some data out there, of, at least anecdotal. And also I should mention that Paula Iannone, I'm sorry, Paula, if I'm messing up your name, but is organizing a conference at the University of Loughborough in a few weeks. And you might want to check that out as well. But so I just want to mention a few of my own teaching efforts in the next 10 minutes in the time I have remaining. So in recent years, I've become a kind of serial textbook writer. So I've written at least 4 kind of lean teaching textbook type things. And so I want to mention 2 that I won't talk about and then 2 that I will. So the 2 that I won't talk about are these. So first of all, Theorem Proving in Lean is a resource out there that's widely used in the Lean community for, it's an introduction to Lean. I've used it in the classroom with undergraduates and graduate students in mathematics and computer science and philosophy. But these are more advanced students, so they already know some mathematics and computer science, and they're coming to learn how to use an interactive proof assistant. And so the focus isn't on mathematics. In fact, Theorem Proving in Lean was written before Lean had any mathematical library to speak of. So it's really about the core logical foundation, the rules of the logical foundation. It's about Lean itself, the system, the commands, and how it works, and so on. Okay, so the focus is on sort of the logic and the artifact itself, and not on mathematics, so I won't talk about that. And last semester, I taught a course at Carnegie Mellon with Marijn Hulle and Wojtek Nawrocki, who is Wojtek is a PhD student of mine. It was called Logic and Mechanized Reasoning. So this target audience was roughly second-year students in computer science. So that was a course on logic and automated reasoning based on Lean. But again, it was about automated reasoning. It wasn't about mathematics, so I won't talk about that. So the 2 I will tell you about briefly, the 2 courses, are Logic and Proof. The 2 textbooks are Logic and Proof in Mathematics and Lean. And the reason why I want to mention both is that they're really two different parts of the landscape. So Logic and Proof I have used in introductory mathematics courses. 2 freshmen and sophomores, so some of them from math and computer science, but in my home college, the Dietrich College of Humanities and Social Sciences at Carnegie Mellon, it fills a math requirement. So, I've had business majors and modern languages majors and so on. So it's really it's supposed to be for students with no background in mathematics beyond high school mathematics, and it's supposed to teach them logic and how to write informal mathematical proofs. So I'll say a little bit about that. Oops, sorry. And then the other one is a textbook that I am working on now, jointly with Kevin Buzzard, Rob Lewis, and Patrick Masseau, and that's Mathematics in Lean. And that's really designed to get people formalizing mathematics in Lean as quickly as possible. So it's really a course that's very much targeted and focused on people who already know some mathematics, and here's how you formalize it. So it's specifically about formalization. Okay. So the goals of Logic and Proof were to teach students how to write ordinary mathematical proofs, and at the same time to teach students, symbolic logic, so propositional logic and first order logic and so on. Not a lot of meta theory, but just the language of propositional logic and proof rules, and informally, semantics, truth table semantics, and so on. And then to teach students to use Lean, but not so much Lean for the sake of using Lean, but Lean for understanding logic and understanding logical proof. Let's see, I'll show you the kind of web page in a second. Everything is online. Well, yeah, let me run through this. Maybe I'll show you the web page in just a second. So the idea is that, on the mathematical side, it's just a concepts of math class, sets, relations, functions, induction, combinatorics, elementary number theory, and so on. So the idea was to make it about as straightforward and unexciting of an introduction to mathematical reasoning as possible. And similarly, as straightforward an introduction to basic logic as possible. The novelty being that, we're doing the 3 of them together. So you're learning some math and some logic and doing Lean. And the hope is that, by combining these 3 languages and 3 ways of thinking about things, that they reinforce each other and help students understand all 3 of them. So let me just say that the textbook is online. If you Google it, it'll probably come up, or you can link to it from the slides. But there it is. There's propositional logic, natural deduction. So there's the logic, and then propositional logic and Lean. So it jumps around. You're either doing logic, or you're doing something in Lean, or you're doing mathematics. But the first 10 chapters are mostly focused on logic, in formal and in Lean. So for example, there's first order logic, the language, natural deduction for first order logic, and then first order logic in lean. And then after a while, the logic falls away, and we're just doing mathematics. So elementary set theory and how to calculate with sets and so on, and then how to do it in lean. And then relations, orderings, equivalence relations, and so on, and then how to do it in lean. And then functions and so on. And we go on for a while. And then finally, towards the end of the course, lean drops away, and it's just elementary number theory, combinatorics, and so on. Okay, and let's see, one of the chapters, let's do one of the ones with lean. So functions in lean. So the way it works is, the textbook is here and you read it, but when you click on one of these things, you actually get a lean window. And if we wait 10 or 15 seconds, I think the first time it's a little bit slower to load. Students can actually do the exercises. They can experiment with the code in their browser window. So it's set up so students can install lean and use it on their home computers. But it's designed so that they can do everything online in the browser. Okay. So yeah, so here are just examples of, we want to teach students reason about equivalence relations. So suppose you have an equivalence relation for every A, square brackets A is the equivalence class of A, so the set of things that are equivalent to A. And, it's the standard exercise, ask students to show that the two equivalence classes are equal if and only if A is equivalent to B. And here you see a student answer, which is, not the best, not the worst. It's, assume, the equivalence classes are equal. This means that the set of elements C and A such that C is equivalent to A is equal to the set of elements C and A such that C is equivalent to B, and so on. It's just an example of the kinds of things that we ask students to do, and they do it, reasonably well. Here's another one. Let f be any function from x to y. Let g any function from y to z. Show that if g composed with f is injective, then f is injective. And here you see an answer, again, a student answer that's pretty good, not great. But this is something you very often see with students, that sometimes they're trying to prove a universal statement. They want to show that for every x, y, and x, if f of x is equal to f of y, then x is equal to y. And they start by saying, now assume that there exists some x and y in x such that f of x equals f of y. But now teaching them logic, you can sort of explain to students why this is kind of a bad way to, you know what they're thinking, but it's a universal statement. You're not assuming, an existential hypothesis. So they can, it kind of helps clarify that. And the point is that they can do a lot of not everything we do, but the simpler exercise they can also do in lean. So this was the exercise we just saw. So here, you're given f from A to B, g from B to C, the hypothesis that g composed with f is injective. And they say, let x1 and x2 be elements of A, assume that f of x1 is equal to f of x2. Then by substitution, g of f of x1 equals g of f of x2. But now because g composed with f is injective, then x1 is equal to x2. Okay. Okay. So yeah, so features of that course, we make it clear to students that we're doing mathematics and symbolic and formal proof. We're doing three things at once, but we keep them separate. But the hope is that, and it seems to, that doing the three things and going back and forth kind of reinforces these different views on mathematical reasoning and helps them understand it better. Okay, in the last 2 minutes, let me just say a little bit about mathematics and lean. So whereas logic and proof was designed for really beginning students, so mathematics and lean is something that we are intending to use this summer for a workshop for mathematicians at ISERM in Providence, Rhode Island. So to teach research mathematicians how to use lean. But I also plan to use it for undergraduate math in a course in the fall at Carnegie Mellon for undergraduate math majors. And so here, let me flash that before you. So here is an online textbook. And it's in progress. So, logic and lean, how to do sets and functions, number theory, abstract algebra. So we're still going. Here, rather than use it online, there's a repository that students are expected to download. There are mechanisms. They can open this up and run it in the cloud. But let me see. Oops. Let me show you a picture of what this. But the intended usage is rather something like this. So here is, the textbook running in the browser. I mean, you don't have to read it this way, but you can. And so the idea is if you're working through this section, you kind of read this section, And then all the examples are in an example file alongside. Okay, and some of the examples now are exercises. It'll say, somewhere, see if you can fill in this, see if you can fill in a proof. And then, and then the readers are supposed to then fill it in. Okay, and so, I know my time is up. Let me just finish up quickly. So the design decisions of writing this textbook are, first of all, don't worry about theory, logic, foundations, anything like that. Just start them in just doing mathematics, right? It starts with just calculation, basic calculation with equality and so on. Oh, sorry, that should say build up gradually. And then you just kind of teach students, you just show them more commands, more syntax, as you go. But the focus is always on mathematical examples, right? You try to teach them how to formalize mathematics by having them formalize math. You start with simple mathematical examples, give them a few commands, they do it, and then keep going. And so it's very much on the model of you read something, you do something, right? Read a few paragraphs, then there's an exercise, something to try, and you keep going back and forth. Okay. All right, let me just finish up. Just one more thing I wanted to mention that. Another thing that I think we should keep in mind when we talk about the, proof assistance and formal methods for education is the role of the community. So people there's a very active Lean community out there, and there's a social media group on Zulip. And it's a very lively place where people come and they help each other, right? So newcomers come and they ask questions, and people help them and answer them. And then these newcomers, a few weeks later, right, they've learned how to use the system. They're answering questions for the next generation. And so you get these communities of people learning to use a system and helping each other. And I just want to mention, just as a parting thought, that if we can figure out how to do this thing for mathematics more broadly, get these mathematical communities where people just get together and they answer questions and help each other. And wow, that could really make a huge difference. So I mean, it's things like, we have things like Math Overflow. There are things sort of like that, but nothing quite like the interaction that you see on Zulip. Okay, so just to finish up, so interactive proof assistance can be a powerful tool for teaching because they give you instantaneous feedback and so on. But there are questions. We need to think about how we can use them with different audiences, and are they really teaching the skills we want to teach? But it's an exciting time. I mean, formal methods are really, have the potential to change the way we do mathematics, and there's a lot of potential for pedagogy, the interactive feedback, the online resources, the user communities. So I think we need to be careful and make sure we're doing it right. But if we do it right, I think it can have a very big impact. So thank you very much.
Thank you, Dr. Avigad, for that talk. I'd like to open the floor to questions. By the way, your video is paused. You might want to start and restop video, but we're happy to field questions from the audience for the next couple of minutes.
Am I there now?
Nothing's showing up on my end.
Huh, but you can hear me.
Yes, yeah, we can hear you fine. And the whole talk was audible. The slides were present, yeah.
Oh, good, okay.
We have a question from Vivian.
Yes, thank you. Thank you for the presentation. I have a question, Jeremy, because I think it's because I am here, it's important to think of introducing these automatic provers in mathematics education, but there is a large body of research on in mathematics education on proof proving and on-proof proving and logic relationships. So I would like to know if you are already connected with this community, or if you intend to connect it with this community, because I think this is very big challenge. If we want.
Oh no, yeah, no, I'm not. I'm here. I want Gila and Kitty to tell me what to do, or you to tell me what to do. So no, I'm on the field. I'm somebody who has used it, used the technology to teaching, and at least anecdotally, I can tell you that the students rate the courses very highly. They seem very happy. They enjoy it. They do well on the exams. So anecdotally, my feeling is this is a great thing. It's a very powerful tool. But no, I don't have I don't have hard data. I haven't done all the things that I know that one should do in educational research to make responsible claims as to the efficacy of teaching methods. So no, this is no, I have not.
I see Kevin Buzzard also has a hand up.
Hi, Jeremy.
Hey, Kevin.
Thanks for the talk. So I thought Stephanie raised a very interesting question about, I mean, what is actually the point of introducing these things into a curriculum at all? Because what are we actually trying to teach the students? Are we trying to, and several of her suggestions, are we trying to teach them to be better problem solvers, or are we trying to teach them to use the system? Or are we trying to teach them to understand that math is built on logic? And you mentioned me as one of the people that are running one of the, trying to use lean in teaching, and I never really asked myself those questions at all.
Yeah.
I just threw myself into it. But I was just wondering whether you had actually done a better job than me and actually
agree.
considered the questions.
Yeah, I raised these questions as well. I think these are exactly things that we should be talking about and thinking about. So as I said, you might be interested in teaching proof assistant technology just for the sake of teaching proof assistant technology. Say that, look, this is something useful in its own right, and so teaching people to do it. And why is it useful? Let's just build these mathematical repositories. It's computer scientists use it for verifying hardware and software. You can point to the advantages of the technology itself. But I think we also have the feeling that, look, this is a good way to learn mathematics. That, if you're learning mathematics, look, it doesn't replace, just going off into the fields and taking a walk and thinking about the concepts. It doesn't replace pen and paper reasoning, but we like to think that it does supplement pen and paper reasoning. That, if you're trying to understand something, well, sit down and write down a formal definition and kind of hack through it. So I think, so yeah, so there are really two parts of it. I mean, one is we really want to be better about articulating what the goals are. It's kind of mathematical thinking and reasoning, and there's kind of an aesthetic, and there's also practical side. So we have to think about what it is that we're trying to get to students. And then there's the real question of, do proof assistants help? And you and I like to think it's got to be good for something because it's so much fun, right? But yeah, no, we should be talking about it.
Great, and I see one more hand from Howard. So this might be our last question for the question period.
I just want to point your attention to a couple links that I posted in the chat. In the mid-30s, like 90 years ago, there was a course taught in Columbus, Ohio, to high school students called The Nature of Proof, that it formed the basis of a PhD thesis that is posted at one of the links there. And it is a profound description of how Euclidean thinking ties into how problem solving exists in the world and how to deal with it. So I strongly recommend anybody who's interested in dealing with the issues of why are we teaching kids these things and the impact it had on kids, because they followed up with the students 60 years later and asked them about the impact of the course. And it is a profound description of the pedagogy and of the influence on students throughout their lives. So I recommend, it's in the chat. There's 2 links there. Anyways, thanks.
Yeah, thank you. Thank you very much.
Wonderful. So we now have a little bit of a 5-minute break for people to get up, maybe grab a cup of tea, stretch before our next talk. So I just want to take another moment, thank Dr. Avigad, thank Dr. Dick for the wonderful talks that we've had this morning, and we'll see people back in about 5 minutes. Thank you very much, folks.
Thank you very much.
Welcome back, everyone. I hope you enjoyed the morning and had a nice break. We are now very fortunate to hear from Paola Iannone and Anita Tama, who are here to tell us a little bit about their experiences with learning about proof with Lean. Over to you, Paola, and thank you so
very
much.
Let me just share my screen. Hang on a second. Sorry, I just use so many I just use so many kind of system for talking to each other these days that I forget how you do this in each one of those, but I found it again. There you are. Okay, so first of all, I wanted to say thank you very much for inviting us. I will be talking about some work which I've been doing with my colleague Atina Toma at Southampton University. The timing of our talk actually is really good because we are in some way doing some of the things that Jeremy was asking for. So from the point of view of educationalists, we go out, we collect data, and we try to answer questions like what impact has this resource on students' learning? Our interest in Lean comes out of two avenues, if you like. One is very much what Viviane was talking about before. There is a very large body of literature in mathematics education that deals with the problems that students encounter when they start university and they encounter proof. In this slide, I've just listed some of them, but the literature is really vast and there is really lots more to this. The other aspect of this is the introduction of programming in university mathematics. And by programming, I mean all things like MATLAB, Mathematica, Maple, Python, R. The introduction of programming is due a lot, at least in the UK, to the fact that programming is becoming a really important skill that graduates must have. So if you like, something like Lean, using Lean for teaching pure mathematics, puts together kind of trying to alleviate some of the difficulties that we have students have with proofs with this idea of teaching programming. We also know that Lean is not really used, again, at least in the UK, in mathematics. I only know of 2 cases. So this is where we started from with our thinking. The third dimension, of course, is the gap between research and practice. There have been several surveys that have been done with mathematicians, and they show that more and more mathematicians actually use computer programming in the research, while only a very small proportion include programming in their teaching. This is this gap between research and practice is really very important, I think, for teaching mathematics at university level. There is a very good passage in Freudenthal's book where Freudenthal describes the struggles of one of his friends when he was doing his PhD, who thought that you would just sit down and a theorem would occur to you, because this is the way that we teach mathematics. We have it all wonderfully prepared, and we kind of proceed with this definition theorem proof mode, which is really quite far away from what mathematicians really do. The other thing which is really interesting is that there have been in the past some attempts to use software designed this time by people like myself, so by educators, to assist with mathematics and with learning pure mathematics and proof. And the example comes to my mind is the example of iSettle that was designed by Dubinsky and Laron. And this software comes with anything you would want it to have. It has very accessible textbooks and exercise sheets. It's backed by a research program that showed that can be really useful for teaching pure mathematics, but nobody uses it. And there are reasons for this, and I think that one of the reasons for this is that iSettle is not part of what mathematicians do, so it's not part of their research. So this idea to try to bridge this gap between research and practice, I also think is quite important. So our first idea when we started working on this was, what is the impact of using Lean on students' mathematics learning? This is a very broad question. So what do we mean by this? We mean the impact on the proof writing, on the proof understanding, on the proof production, so in thinking how to structure the proof, on the clarification between the technical mathematics and computing this time and the natural language. the impact on their perception of mathematics, so bridging this epistemological gap that we know exists between a school and university, what reasoning skills are fostered by Lean, effective reactions to using Lean. This is also part of learning. Do students perceive that this program is just so difficult that it's just impossible, they don't want to use it? In some way, this responds a little bit to Jeremy's question, is this something for everybody or is this just for the very brightest? So this was the first question that we asked, and the way we operationalized some of these questions in 2 studies, one which we finished, one which we are currently doing. And in the remainder of this talk, I will show some of the results of the studies. I will not kind of deal very much with issues of methodology and analysis, because if you want to read those, you can go and read the papers. But I want to point out to some of the things which we found and why we think that this data shows us some things regarding what is the impact of using Lean on students' mathematics learning. So we have 2 questions that we wanted to ask with our research study, the first one. And the first question was, what characteristics are observed to be common to proofs by students who engage with Lean? And the second one was, what are the barriers students encounter during the engagement with Lean? So the idea of the first question was, if we take a bunch of students that have engaged with Lean consistently, and a bunch of students that have not in the same class, so comparable background and comparable previous experience, and we do them a proof of an unseen task to do, are the students that use Lean producing proofs which are qualitatively different from those who are not using Lean? And we'll see what we found regarding that. The second question was regarding uptake. So what are exactly the difficulties that students find in using Lean? And what is the result of the engagement with Lean in terms of what are their beliefs about mathematics, about what is mathematics and how mathematics in some sense is produced? So in order to try to do this, we work in a year 1 module, Foundation of Analysis module, very standard UK module, 3 hours of lectures per week, weekly seminars. But in this module, Lean was not a compulsory part. And this is something I will come back to also later. So the module was structured in a way where Lean was part of the teaching. So the Lean proofs were shown during the compulsory lectures, and there were optional Lean sessions, but the Lean sessions and kind of the learning about Lean was not compulsory part of the module. So students could go through the module just normally without ever engaging with Lean, although they would see it in lectures. What we did, we interviewed 37 students in talk aloud technique. So we gave them some mathematical tasks, some seen and some unseen. And we asked them to solve these tasks in pen and paper. And in the process of solving these tasks, we asked them to talk about what they were doing. Today, I will talk about some of the proof to this task. We gave them the definition of an abundant number, and we asked them to talk about this task. If n is perfect, then kn is abundant for any kn in n. And under there, I have a solution of the task. The reason why we gave them an unseen task is that we wanted really to be sure that the students couldn't remember the proof. So they couldn't say, oh, I've seen this somewhere, I'm now remembering how to do it. So we wanted to be sure that the students really engaged with a proof construction task, if you like. So they had all the tools to be able to solve this proof, which is not too difficult. And we asked them to talk to us whilst they were doing so. So we analyzed the data in 2 ways. We did not want to talk about attainment. So we did not want to say the students that take Lean classes perform better. We could not say this given the structure of the module, and this wasn't the aim of our course. So of our study. So what we did, we asked a mathematician completely outside the project who knew nothing about Lean or the students or anything to score the proofs from 0, where there was no attempt done, to 4, where there was a proof that they considered complete and correct. And what we then did, we compared the proofs at different score levels. So we compared proof that scored 4 and 3 and 2 and 1. And then we coded them according to this class, these aspects of proofs that are that Fulham Connolly talked about, and they're quite kind of standard ways of looking at proof in the mathematics education literature. And what I want to do now, I want to show you some of these proofs. So this is the second part of the proof of two proofs that scored 4. So these are proofs that were scored as good proof by a mathematician. And this that I'm going to show to you is the second part of the proof. So the students had written already something to begin with, so probably the definition of abundant again or something, and they write the body of the proof. So this is the part of the proof, if you like, where the real problem-solving task starts. So I'll give you 1 minute to look at this. I hope you can see the screen okay. So by just looking at this, I think you can see that this proof looked different. And the obvious first difference in the proofs is this one. So in the proof on the left-hand side, there is a clear breakdown in goals. In this proof in particular is really kind of even tagged. You have a lemma 1 and you have a lemma 2 and you have a lemma 3. This is, we hypothesize, coming directly from the experience of having to write goals and sub-goals in Lean. And this is a Lean user, the student. On the right-hand side, this is a correct proof. So if I was to mark this proof as part of coursework or as part of an exam, I would say this is a correct proof, but it's not organized in the same way. And as I said before, on the left-hand side, we have a Lean user, and on the right-hand side, we have a non-Lean user. So if we go in for kind of the start of the proof of students that scored 3, so the proof was okay, but it wasn't perfect, we can see other differences. So on the left-hand side, you have a much better use of mathematical language. The thing that got us is that we could see that with Lean students, you would even have, words, you would have punctuation. You can see that you can see full stops. You can see kind of mathematical language used in a much better way. Whereas on the right-hand side is something that is more similar to what I see when I mark these kind of papers. And again, on the left-hand side, you have a Lean user, and on the right-hand side, we have a non-Lean user. If we go ahead with proof that scored really quite badly, so with students that did some attempts, but they couldn't not really go through, and I show you these proofs, we can see that on the right-hand side, I had a mathematician colleague in my previous institution that used to call things like this random mathematics. So you have something that looks like mathematics, but it doesn't really follow any logic structure that we would recognize. And again, this is quite kind of unfortunately common performance of students in the first year. On the left-hand side, though, you have something that is also not correct and also doesn't go anywhere. In fact, the proof ends at the end of what you see. But there is an overstated attempt to formalize. You can see an Iverson bracket here. You don't need this to do this proof. And what we found is that on the left-hand side, you have a Lean proofs where in the attempt of formalizing lost track of what they were trying to do. And on the left-hand side, you have a confusion in mathematics, if you like, so something that doesn't really make sense. So if we, after the analysis of the data, we found that there were some things we could see that were common to students who used Lean. And this concerned the use of technical mathematical language and symbolism, the explicit statement regarding where certain mathematical objects belonged. So in the proof by Lean users, there were always statements. So there wasn't just let n, but there was always let n in the natural numbers and things like this. There was a lot of attention to actually trying to write sentences in full words and full stops and so on that we didn't see in the other proofs. And the proofs were structured differently, if you like, in goals and sub-goals. So this first study, which obviously is not a large study, is quite encouraging because it seems that the answer to what Jeremy was saying before is yes, some of the habits that Lean kind of brings to the users do transfer to doing proofs on pen and paper. But there are other dimensions to this. So what are the barriers and the affordances of using Lean? So in the same module, in the same year, this was 2018, we gave a questionnaire to students. We had 99 returns. And in the interviews I talked before, the last part, we discussed the students' use of Lean. What we found is that the vast majority of students, for them, Lean was too difficult. And it was not worth investing the time. And only a very small fraction engaged with Lean consistently. It's really interesting. So Jeremy was talking about having fun when doing Lean. And fun was one of the adjectives that was most associated with the experience of Lean from those who did engage with it. So these are the numbers on the right-hand side. The students told us that time constraint didn't allow them. The difficulties of the programming language was a barrier. Some were just not interested, and some of them still used Lean. In the end of the teaching period, it was actually, I think, only 18 students who engaged with Lean consistently. Barriers to learning were syntactic. It's really hard to learn the syntax of Lean. One of the students told us it's hard to remember all the commands and it's really different from normal maths. There were strategic difficulties. So knowing how to use the shortcuts, how to use the tactics and all this kind of stuff. And there were some conceptual difficulty. So the students tell us, I don't know if it's good or bad, but like sometimes I don't see the whole picture of the proof. I just look on the screen and I have to prove this. And I don't know how to prove this. It's really interesting though, because these three barriers to engage with the programming language are what also the computer science education literature tells us. What we observed is that the conceptual difficulties were not just conceptual difficulties related to the use of the program, but were conceptual difficulties related to the mathematics that was the subject of the use of the program. However, we found that the biggest barrier to engagement was that the students could not see the link between what I have here on the left-hand side and what I have on the right-hand side. So what I have in this slide, we have just the code of Lean for the sandwich theorem, and on the left-hand side, we have a writing up of proof of the sandwich theorem. Many students did not see why, if I wanted to write a proof of the sandwich theorem, I should have to engage with this programming task, which they found incredibly hard. In fact, one of the students told us, I don't think it would be beneficial. I would rather spend my time doing mathematics by myself instead of trying to write a code. Lean is useful if you're interested in computer science. And this was really a barrier. So my suggestion would be that if you want ever to use Lean for mathematics teaching, we really need to make sure that the students know why we are doing it, because a lot of the students here seem to not make the connection. So where are we going next with all this? Before where we're going next, to those students who engage with Lean, we observed something really interesting, and the idea, our observations was that their understanding of what is mathematics changed. Now, this is important because that literature on proofs that we were talking about before has pointed out very often to this, we call it this epistemological crisis that happens when the students join university. So suddenly they go from thinking about mathematics as a set of procedure to be faced with all this idea of proofs and abstractions and rigor, and to something that they don't recognize as mathematics. For these students who really engaged with Lean, they seem to get it at that point. So they told us things like, we asked them what we learned about Lean. Why do you think that Lean could be useful? They told us things like proving everything, or I enjoy finding out where maths come from, or I learn how to prove intuitive things rigorously. Or one student even told us it made me reevaluate my view of mathematics. Now, if this was one of the outcomes of using Lean, this obviously would be a very good outcome because it would help students making that transition from school into university mathematics. So what are we going next? At the moment, we are doing another study on student reasoning while using Lean, so while solving tasks in Lean. We are currently trying to collect data, not very successfully. Students are becoming harder and harder to catch, where we are giving students a half-coded Lean proof, and we ask them to solve them in a think aloud interview, and we also ask the students to first do a proof in pen and paper and then do the same proof in Lean. So you have an example here what we are using, and these are examples that Tina put together. And the students first do the pen and paper stuff, and then they tell us how would they do this with Lean. We've only interviewed 4 students so far. We hope to interview more students as the semester goes on. But we observed that the majority of the students don't look back at the pen and paper proof when they prove in Lean. And this may be an indication that I think about these 2 tasks as 2 separate tasks. They rely much more on monitoring what the goals change in Lean, in the Lean interface, and what the error messages say. And also, we don't recall the Lean tactics that refer to the lecturer online resources. And this is really interesting because this is all everywhere in the computing science literature, where that say that this is how people, not generally just students, but also programmers, learn how to program. Whenever there is something, they kind of go in the online resources that they have available. And our students did the same. So hopefully we will be able to collect more interviews to kind of do like a broader analysis. So the final open questions that we still have are, or some of the open questions we still have are, what types of reasoning does programming proofs in Lean entail? What is the interplay between rigor and intuition in this activity? Remember the proof that wasn't very successful, and there was this attempt of being extra rigorous. Is that getting in the way of the students having an intuition of what the proofs look like? Connected to the question above, what is the role of example when programming in Lean? We know that examples have a very big role when doing proofs. A lot of us reason on examples when we have an idea. And finally, what is the role of resources? What helps the students? So thank you very much. And this is a little plug for our meeting that we're going to have at Loughborough University in about 10 days time on Lean. So I think my time is finished, and I will stop sharing the screen, and here I am.
Thank you so much, Paola. That was really interesting. We appreciate it. For people in the audience who have burning questions, as I know you do, please feel free to add them in the chat, and we'll try to keep up with them. But there is also a good chunk of time for discussion at the end of our next 2 sessions, where we will be inviting our speakers to sort of come back and address any questions you have. So thank you again. If we could take a moment to thank Paola and Anita. Very interesting. And we're going to branch off from that talk with another look at using Lean, this time in teaching.
I think Jeremy has a question.
Oh, I'm so sorry. The program is pretty tight right now. We're going to keep questions in the chat box just for now, but Jeremy will absolutely come back to you. So thank you so much. We do have a packed afternoon with lots of good information for everyone. So up next is Heather Macbeth, who will be telling us a little bit about her uses of, her uses of Lean in teaching real analysis. So thank you so much, Heather, and welcome. Oh, you're muted, and I guess let me see it. Make sure you have ability to share your screen.
Heather, you've just gotten co-host access. You should be good to go.
Thank you. Yes, I think I can talk now. So I'd like to say thank you for the invitation to talk here. I'm a mathematician, and I'm not practiced thinking about my teaching philosophy, and it's really been a pleasure to have this excuse to think about somehow the practice of teaching from a new way. So it's been a lot of fun for me to prepare this presentation. I teach at Fordham in New York City, which is a liberal arts institution with, in the math department, only an undergraduate program. We do have graduate programs in other subjects. And I have been teaching with proof assistants for a couple of years now. I started in a different language. This is the language Club, which is a similar language to Loon in spring 2020, with a couple of students who wanted to take real analysis in the off semester and who studied it privately with me and who were both computer science majors. And I took that as an opportunity to explore the language at the time I was also a beginner. Then in fall 2020, I switched to Loon and I ran a real analysis course with some optional Loon exercises. This semester, I've been running Intro to Proof with optional Loon exercises. And finally, next year, I've got the go-ahead from my university to go ahead with Introduction to Proof with mandatory Loon exercises. So I think there's a big difference, as I think Paolo was just explaining, between perhaps the attitude of the enthusiasts and the attitude of the class as a whole, which I'm sure I'll encounter more about when I have the experience of really forcing it on everyone. This semester, I've had the most sort of wholesale introduction of Loon that I've tried so far, in that in addition to offering extra optional homework exercises, I've done it from time to time in class. I spent one lab at the start of the semester and then later labs from time to time, just for a few minutes as part of a regular lecture session. So that has been my main opportunity to see what it looks like for the average student as opposed to for the enthusiast. So as I would have described my teaching philosophy, for these same courses, as I've taught them in prior semesters before I tried to bring Loon into them, my teaching philosophy is quite literal in some sense. I place a high premium on students being able to construct proofs which are somehow literally correct. I penalize heavily students who write things which contain the right idea but are not actually mechanically correct. I place a high value on the mechanical correctness of the proof that's being written. And so you think in some sense that I would be the perfect candidate for that reason for using a proof assistant in education. Something else that I have always really valued is the idea that getting somehow a direct, efficient proof is important. Motivation can come later, that's always been my point of view. And the skill that is sort of unintuitive for students when they first encounter proofs is the idea to really refine what you write until it's a direct, linear A to B style of argument. I like to tell my students that what we want is something that is easily checked, rather than necessarily something that's easy to see how it was invented. So that's the place I'm coming from. And those are the goals that I brought into my experiments teaching with Loon. So from this point of view, I'd like to make the point that the two courses I've been teaching are quite similar. So both of them I teach in a way that are sort of number heavy, variable heavy, equation heavy. And I would contrast this perhaps with, I think, some other ways that you could take to Intro to Proof in particular. It's very easy to teach Intro to Proof with propositional logic, with sets and functions and relations. And I think it's possible that both Jeremy's course and the course of Kevin's that has been studied by Paula have a little bit more emphasis on this second point of view. Whereas somehow in the sense of Jeremy's two philosophies of mathematics education, the theoretical and the practical, I'm really on the practical side, dive in, work with the equations and illustrate the techniques in context. And so from this very literal point of view, the examples I'll be covering in this talk, some of which come from Intro to Proof and some of which come from real analysis, are similar in that they both feature this manipulative calculational style of proof. So here's just before we dive in, an example of the kind of proof teaching I do, and what I like and what I don't like. Here's a problem which I actually covered in class just yesterday. So I wanted to prove that the set of natural numbers for which n squared is less than or equal to 3n plus 2 is not contained in the set of integers for which 2 does not divide n. And so what I try to train students out of is the style in which you first explore and you analyze one set and you identify that the elements of the first set happen to be the numbers 1, 2, and 3, and then look for a counterexample within that set. So this is how students tend to come up with this kind of thing, and I like to draw the distinction that instead what you want to do is to start with the answer, forget about explaining how you came up with the answer, and justify in a very literal-minded sense, why that is the answer. To take an example from real analysis, so here's a classic epsilon delta problem. I have to prove that the limit of 1 over x is 1/2 as x tends to 2. And I think something that students in real analysis find very hard at the outset is this, given the epsilon, how do you find what the delta is situation? And I've seen textbooks, I've even used textbooks where the proofs are presented in this way, that I think explains how you come up with the delta. You do as much of the calculation as you can. You get to the end, you have a bound, you keep note of all of the things that you needed to get that bound. In this case, you at some point assumed that the difference between x and 2 is less than or equal to 1, which does you no harm. And then later, you observe that you also needed to be less than 4 epsilon. And then you sort of discursively introduce the delta as the mean of 1 and 4 epsilon at the end of the proof. And I really prefer the style where you start with your epsilon, you say what your delta is, and you calculate it. So this is the kind of thing that I try to teach my students, and therefore it's the kind of style I was trying to enforce for the students working Lean as I started using Lean. So in some ways, this meshes very well with Lean. So in Lean, it's very easy to modify a proof once you have a proof. It's very easy to rearrange a proof. It's very easy to test whether you ever sort of used a fact that you proved along the way. You can simply delete that fact and see if a mistake happened. You can also remove a hypothesis, and that gives you an error in the place where that hypothesis would have been used, if indeed it was used. So this kind of exploration is great as far as my goal of efficiency is concerned. It's easy for students to play with their proofs and to try to rearrange them to get the most direct presentation in the end. On the other hand, one problem that I found using Lean with my students is that idiomatic Lean is quite non-linear. So the way that students, not just students, but the way that experts even interact with Lean is quite non-linear. You sometimes work on the goal, you sometimes work on the hypotheses. Sometimes you reason forward, sometimes you reason backwards. And the tooling that is available in Lean is written by experts for experts and supports this non-linear style, which means that sometimes if you're trying to force a forward style on your students, you find that the tooling is not set up to support it. So just maybe to justify why this non-linear style, which is from a written sense not sound. If you're programming, it's just faster to say I'm going to apply a certain theorem to the goal than to have to apply a theorem to a known fact and say which of the known facts you're going to apply it to. At any given point, you have just one goal, and you have many facts that you might want to apply that theorem to. Or likewise, if you've got an equality that x equals y, if you say rewrite by x equals y in the goal, that's unambiguous. Whereas specifying which hypothesis you want to change x equals y to it becomes more cumbersome. So from a coding point of view, it's faster just to work backwards in many situations. On the other hand, as we as humans present a written proof, it's less fast. And the reason is that when we change a goal, the convention in human writing is to say what the new goal is after applying a theorem to that goal. The reason is because when you're writing, you don't have the tactic state that Iannone was displaying. So the division of the screen into two, with the writing on one side, the proof itself, and on the left, the visual manifestation of what is happening to the hypotheses and goals. You have that aid to the reader is not present in the written proof. And for that reason, it's the convention in good mathematical writing to write in a style which keeps track for the reader of what your current hypotheses and goals are. If you're constantly, modifying goals and hypotheses in place, the good style is to write out again those hypotheses and goals. And that becomes very cumbersome. And so good mathematical writing becomes something in which the tactic state on the left of the screen hopefully is secondary. So because of this, I found myself trying to design and teach Lean to students in a way that more closely mimics what I would like to see them writing. And I'll mention, although I don't know too much about this, that there's a related debate among theorem proving experts about the relative merits of procedural and declarative proof style, if you want to Google that. So I try to design exercises for students in which there's a common pattern of stating a goal and proving that goal immediately, either directly using the Lean have style, where you say the word have and then you state the thing that you're going to justify and you justify it in one step, hopefully, or alternatively by a calculational environment in which a transitivity proof is justified step by step. And I'll give an example of that on the next page. So for the Lean experts in the audience, my slogan is to ban the rewrite tactic. So here is the kind of thing that I would treat as my goal, the kind of situation where what I would like to see the students writing on paper and what I would like to see the students putting into Lean matches as closely as possible. This is a simple number theory proof. I want to prove that given an integer n, if 8 divides 5n, then 8 divides n. And the proof is to produce the witness, which is the number minus 3a plus 2n, and just get down to it. And as you can see, what I like about this proof is that it translates directly to Lean. You might not know Lean, but I hope that you can see that the left and right sides of the screen have a very close correspondence. And the tactics, so those are the words ring, RWA, and ring again being used, are perfect tactics for justifications of single steps. So this is the goal as far as I'm concerned. One thing that I already notice when showing this kind of thing to students is a problem which I'll mention for the Lean experts, which is that this calc environment that I'm using in this proof here is unusually unfriendly to use for newcomers. There are a lot of very subtle bugs that come up when you're trying to write a proof in this calc environment. In fact, I think that expert users often come up with a proof in some other way and then rewrite it later to the calc environment for presentational purposes. So it would be wonderful to have more robust versions of this calc environment, even a point and click version, which confuse the students less. I think students are constantly encountering errors as they try to use this calc environment, and it would be great to have dedicated effort by someone who knows what they're doing to make that environment more user-friendly. So I want to now talk about some problems that you encounter when you try to keep this style of proof in slightly more mathematically complex situations. So the key thing here is that I want to try to stick to problems where one human step is one lean step. And that requires automation. And in many cases, as you saw before, it already works to have one human step to one lean step. But in some cases it doesn't. And even in some cases, and I think this actually comes up more in teaching practice than it does in usual sort of research learning practice, for two reasons. One of which is that there are things that you commonly want to do when teaching that are just, not research, not a standard technique in research level mathematics. So on the next slide, I'll be talking about modular arithmetic. And, as a working mathematician, I never use modular arithmetic. This is a fun thing we teach to students, but, I myself don't reason about things modulo 3 on a daily basis. And so we just don't have the tooling set up in Lean to support modular arithmetic. I guess it could be added. It would be nice to add it, but it didn't exist already. Another problem is that it might be possible to do something in one step, but when you try to do it in one step, you actually realize that it can do the whole problem for you, or it can do several steps of the problem, and it's not ideal for that reason. The tactic is just too powerful. And so it's not pedagogically useful for that reason. The student can't follow what's happening. It covers, in one step, things that take the student several steps. That's also not ideal. Or it may be something related to that second point, but not quite the same, in that it may be that it's one step, but it takes a more abstract point of view to come up with that one step than the student wouldn't necessarily realize. I haven't prepared an example on a slide, but the kind of thing I'm thinking of is, you might, as an expert human mathematician, see that the thing you're trying to prove comes from 3 copies of equation 1 minus 1 copy of equation 2 after some rearrangement. So a kind of linear combination argument. And this is supported by Lean's new linear combination argument, written by one of Rob Lewis's students at Brown. But expecting a student who hasn't taken a linear algebra course to come up with the idea that, an equation is a linear combination of 2 other equations is obviously unrealistic. So you need to deal with situations where the one-liner that we have for humans is not the one-liner that a student would have at this level. So here's the kind of modular arithmetic problem that is one step up from the problem I was showing before. Something that, with a bit of effort, I could get working perfectly in as far as I was concerned. So this is a problem to show that for an integer, 5n squared plus 3n plus 7 is odd. So, there are fancier ways to do this, but the naive way that I wanted to do it was to say, we have 2 cases, case 1 when n is even, case 2 when n is odd. And in those 2 cases, we have a different remainder modulo n, modulo 2 in each of those 2 cases, and we just calculated it. So when I tried to write this in Lean initially for the use of my students, it didn't work. And the reason is that this deduction that 5n squared plus 3n plus 7 is congruent to 5 times 0 squared plus 3 times 0 plus 7 modulo 2 is actually a combination of many facts. You need a theorem about how addition behaves modulo 2, a theorem about how multiplication behaves modulo 2, an argument about powers modulo 2, and all the way through. So the students will interpret this as a pure substitution argument. And I know this because when I talk to my students and I ask them to explain their proofs to me, they'll say something like, we substitute n congruent to 0 modulo 2 into 5n squared plus 3n plus 7. And this is not a valid substitution because n is not equal to 0. Instead, it's only related to 0 by some relation. But the students experience it as a substitution. And even we teachers present it as a substitution, in that we present it as a single step of argument, along the lines of a substitution, matching very closely the kind of thing we would do with an equality for a substitution. And so I have written, in very happy private code, a tactic that carries that out as a substitution. It really applies all of the lemmas about addition, multiplication, powers, and so on, modulo 2, and then tries to apply the stated lemmas, in this case, the hypothesis Hn, that n is congruent to 0, to resolve anything that remains after applying those lemmas greedily. And as you can see, after that, it is possible to write a Lean proof that matches pretty closely what the paper proof would have been. There's a second tactic here, which I won't say much more about, which is the tactic of splitting interfaces modulo 2. Again, this is just the kind of thing that researchers have never needed and therefore didn't previously exist in Lean. I just want to check, how much more time do I have? Is it 12:25 or 12:30?
12:25.
Thank you. So to get on to now, when things become yet more complicated. The same thing applies crucially for real analysis when you're reasoning not about the relation of congruence modulo 2, but about relations of inequalities. But the corresponding problem is much harder. So to justify inequalities, you have a much broader range of lemmas that you might need to justify why a complicated expression is less than or equal to another complicated expression. And many of these are not, they don't apply automatically, instead they have some side conditions. So for example, you might need to apply the lemma that AB is less than or equal to AC if B is less than or equal to C, but notice that what I just said is not actually a lemma. It's a lemma only under the hypothesis that A is greater than or equal to 0. So you might set up your automation to try to apply this lemma, but it will generate this side condition that A is greater than or equal to 0, which then you need to either present to the student as a side door that's been created, or you might try to solve it itself. I mean, that would be ideal, but again, might not follow if the student doesn't set up the problem in the right way. And it's even worse because the student, you might be in a situation where AB is less than or equal to AC because B is greater than C, but also A is negative. And so there are two lemmas that might apply, and you have to decide whether you're going to rigidly apply the more obvious of the two, or to allow for either of them under some user interaction situation. Then there are things like absolute values where the behavior is highly non-obvious and under less than or equal to relations, and a whole lot of sort of special case one-off things like that. So all I'll say here is that the automation problem is hard. I think there's a lot of work to be done here, but it should be better to do than we have already. Here's a sample proof from my real analysis course, and it really matches a lot what I think Paula was saying about how, the students have to spend a lot of time on things that do not seem to them to be closely related to the important part of the problem. Here I've got an inequality calculation, the calc environment at the bottom of this slide, where every line is justified by its own one-off, random approach. They're all different tactics. Some of them involve clearing denominators. One of them is a nonlinear inequality supported quite randomly by some other fact applied to a certain thing. There's a specific lemma about absolute value multiplication. Writing automation to help here is hard. And I found, therefore, when teaching real analysis, which is an absolute forest, an absolute thicket of proofs like this, the learning curve is very, very steep. So there's just somehow too many things that you need to allow for. There are very powerful tactics such as n-linearith available, but even to the experts, it's not always clear when one of these tactics will work and when it won't. You need to have a very precise understanding of its powers. And there are also sort of, in regards to this dependence on particular lemmas over and over and over again, there's a tactic called library search to find these lemmas from the main library, but it's fragile and it will miss something that follows from an obvious combination of two lemmas. One more final point in my last 30 seconds about infrastructure. So you need to make the infrastructure as foolproof as possible. I borrowed Jeremy's idea of using in-browser lean coding environments, which is wonderful. And I also really encourage the use of an autograder to guarantee somehow to the students that that they will get, that if they solve the lean problem, they really do instantly get those rewards for the problem, that credit showing up in their credit for the course. This is nice to set up. I've written some hacky code to do this in Gradescope, and I would also like to call out the work of Matthew Ballard, who's done a much more professional version for GitHub Classroom. And that's all. Apart from, I'd like to mention in the ideal case, how it can be experienced by the students. I've had at least one student, a few more, but you know, some students who liked it and a few who really took into it. And in those, I think, in those small number of cases, the experience can be transcendent. It can really help them get to a new level of understanding of mathematics, which I think is what we all hope for from this technology.
Thank you so much, Heather. That was another wonderful and informative talk for us today, and a great positive note to end on, which we appreciate. It's my pleasure now to introduce our last session of the day. From our organizers of today, Gila, Hanna, and Kitty Yen. Thank you so much, first of all, for putting together the session, but also for your sharing your own work on teaching proof with interactive theorem provers in Ontario. Thank you much.
Thank you, Amy. Can everybody see my screen and hear me okay? Yeah. Okay, so thank you all for joining us today. After hearing from our colleagues in the UK and the United States who have done extensive work with theorem provers, especially with lean, you might wonder what's the overall picture of the ITP use in Canada. On behalf of my research team, I'm pleased to report what we've done at the early stages of our research project. Before I get into it, let's first welcome Gila to introduce the research team and speak about the objectives of the project. And Gila, I get the slides ready for you.
Yes, we are working on this project, and our team consists of Kitty, myself, and Kitty, who has a special interest in mathematical reasoning and proof, of Jacqueline, who has a master's degree in mathematics and considerable teaching experience. And then we are honored and privileged to have associates to our project. And from the philosophy of mathematical practice, we have Brandon. From undergraduate mathematics teaching, we have Jason. And from the Lean project, we have Logan and Yuri. We are very grateful for that. Plus, we are constantly consulting with our international group on proof. It's the group that Viviane mentioned before. You can move on to the next. Yeah, now the project, we are working on a 3-year project to introduce Lean to the curriculum. And our guiding principle is to place an emphasis on proof as explanation and to enhance understanding of proof. So we want to introduce a new approach to teaching. What is important here, it's an approach that is reflective of the growing use of digital technology in mathematical practice. We want to investigate the use of Lean with a view to determining its implications for teaching. And we want to test the hypothesis that it is useful to have an additional tool in teaching with the potential to foster mathematical understanding and student competence improving. But we say that existing tools and methods should continue to be used. Of course, we are just adding a tool. We're not replacing anything else. So we hope that the research will offer new insights into effective methods for the teaching and learning of proof. Back to you, Kitty.
Thank you, Dila. Okay, so now this is the outline of the talk. I will first share with you the results of 2 questionnaires. One concerns the views of mathematicians who have used ITPs in teaching. The other is about the current use of ITPs in Canadian universities. Then I will talk about the Lean seminar series we offered to undergrad students and the follow-up interviews with some of the students. I will also briefly talk about our plans for the summer and the fall. So our research project started last summer. Before we planned out anything, we first contacted mathematicians around the world who have used ITPs in their teaching. We want to learn from their experiences and insights into teaching with this new technology. In the end, we received 9 responses, 3 from Europe, 6 from the United States. We happened to get more responses from the States than from Europe. So the numbers don't suggest more mathematicians in America than in Europe use ITPs in teaching. So we asked, the first question we asked for the mathematicians was, which courses do you teach with an ITP? As you've learned from our guest speakers, ITPs have been mainly used in undergrad math courses, including Intro to Proof courses, Computer-Assisted Logic and Proof, Discrete Mathematics, Real Analysis, and also in an Intro to Logic course at the graduate level. We also asked mathematicians about how ITPs were used. They were mainly used to demonstrate a proof in a lecture. Some mathematicians use an ITP for in-class activities or exercises, and also for homework or assignment, depending on how much weight an ITP takes in a course. For example, one instructor dedicated 5 out of 35 class periods to the Lean theorem prover. In those 5 class periods, about half of the time was devoted to Lean demonstrations to introduce new concepts and worked examples. The other half of the time was spent on group problem solving in Lean. And there were 5 homework assignments involving Lean, following up on the 5 lectures. Lean, however, was not included in any of the tests or exams. How was the learning curve for both instructors and students? This is one of the biggest concerns for many instructors who are thinking about having an ITP component in teaching. Here are the responses. For those who already use type theory in research, as an instructor, the learning curve could be rather flat. The learning curve could be also flat for those who have some programming experience. However, without prior programming experience, the learning curve was steep initially for both instructors and students. One instructor pointed out it's not that easy to assess the learning curve. It is a fine point. Let's say a student experienced some difficulties with Lean. A question we want to ask is, where did the difficulties come from? Was it from the ITP or from the mathematical content they had to grasp, or was it from the combination of the two? The answer to that question depends on each individual learner. Therefore, it might not be a good idea to draw a general conclusion. What worked well in their class with an ITP? The mathematicians told us that using lean made the materials less dry. Less dry because students have an opportunity to experiment in lean to figure out a proof instead of the instructor doing a proof on Zoom or in front of the classroom. As a result, it leads to enhanced motivation in learners. ITP also worked well, if not best, with mathematical mature students. One mathematician put it this way, good students really learn a lot. Some average students are also pleased, but weak students don't get anything out of it, even when they get decent grades. Despite students' mathematical maturity, one thing that worked particularly well was that lean forces students to organize their thoughts. In other words, less muddy thinking, more analytical and structured thinking instead. There were some obvious challenges that students have faced in using and learning an ITP. First of all, as the previous speakers mentioned, the necessarily rigid syntax. A lean proof is often not readable for a beginner. This can be frustrating. Secondly, learning to use an ITP is to learn an additional language on top of formal logic and mathematical language. So for example, a lean proof that false implies 0 is equal to 1 looks like this in lean. It uses the intro, ex-fossil, and exact tactics. Without knowing these, what these tactics do, the proof is completely a foreign language. Lastly, translating a mathematical statement for lean requires students' good understanding of that statement. So using lean to prove a theorem is essentially to give instructions that lean understands so that lean uses definitions and verified proofs in the lean library and proves a mathematical result for us. A precondition to do this is to understand the structure and the logical inference of that proof. And this is a challenge for many students, although it is in fact a benefit of using lean from a pedagogical point of view. Now let's move on to the current use of ITPs in Canadian institutions. We sent out emails with a short survey to 26 mathematics departments in Canadian universities. The email gets circulated in some universities, but perhaps not in others. So for this reason, what we're showing here may not be an exhaustive list, and the numbers could be conservative. In 5 universities, 3 faculty were using lean in research. 1 faculty was using AIEd in teaching, and the 2 faculty were interested in lean, but haven't started to use it in their work. For logic courses, some faculty used the Carnap or Logic 2010, which are popular software to do pure logical proofs. The current use of ITPs in Canada is very limited. However, there are faculty and undergrad students interested in getting involved in formulating undergrad mathematics and in learning new things about ITPs. This brings me to the next part of the talk, the lean seminar series we had at the Maths department at University of Toronto. From mid-November to mid-December and on February 9th, we offered 3-session lean seminar series to undergrad students in the math department at U of T. All sessions were online. The 3 sessions were repeated due to multiple campuses at the university. Each session was attended by students and faculty in the range of 14 to 25 attendees. What did we work on with undergrad students in the seminar? Well, in the first session, we started with a brief introduction to Lean. What is it? What does it do? Why does it matter? We also demonstrated a Lean proof to show students how it can be proved in the system. After that, we engaged students in solving a family murder called Melissa and Alice that is available on Jeremy's Logic and Proof website. It is a challenging puzzle and it takes some time for students to arrive at a solution. Then we looked at existential and universal quantifiers with some examples. Some leopard has spots, some birds cannot fly, and a challenge for students to do was to translate a well-known quote by Abraham Lincoln using quantifiers. Then we worked through piano axioms with students to prepare them for the natural number game, focusing on mainly on the 5 axioms of number theory. Then we started the natural number game. It was developed by Kevin Buzzard at the Empirical College London, who's in the audience today. Thank you for making it available to all of us. It is a wonderful game to start with for beginners. Since it's accessible online, we invited students to start off and ask them to continue on with it after the seminar. So now we move on to the second session of the seminar series. We first revisited the Melissa and Alice puzzle, focusing on pattern of reasoning. After that, we review the tactics and theorems that are useful for the natural number game. We also demonstrated a Lean proof using the raffle, rewrite, and induction tactics. And for the second half of the session, we played the natural number game, focusing on the addition and multiplication worlds. In the last session, we first looked at different Lean proofs of the same lemma. If you play the game yourself, you will notice that sometimes your proofs are different from the solutions provided by Kevin. For example, here are 2 proofs of MathEd, the distributive law. This is in the natural number game. So both proofs use induction, but with a different variable. And one question we could ask students is, how about doing induction with t? Would that work? Would it get you into trouble? And there's something to think about. Here's another example. The proof of m times 1 is m. One proof used induction and the other didn't bother. Students quickly notice that part of the proofs in squares are exactly the same. This suggests that the induction works, but it's unnecessary. Comparing different Lean proofs of the same lemma or theorem helped students reflect upon what they've done so that they could be better at the rest of the game. After comparing different proofs, we focused on proof by contradiction. We demonstrated 2 Lean proofs. One is simple, to prove not P is P. And the other one is more mathematically interesting. It is the proof of the infinitude primes. After the seminar, some students told us that this Lean proof of the infinite primes is a good motivation for them to play with Lean and try more challenging proofs. For the rest of the third session, we reviewed the tactics and theorems in the proposition world. We continued on with the natural number game. And we did more proofs on the Lean web editor with students who had finished the natural number game on their own. After the third session, we asked students to complete a short survey about Lean. We received 12 responses. Here are their responses to some of the survey questions. The majority of the students enjoyed trying new things on Lean. They favored the immediate feedback that Lean provides when they were working on a proof. When asked if a Lean proof is more rewarding than pen and pencil proof, most students had reservations to give a yes or no answer. Well, in what sense it was or was not rewarding? This begs more specific questions and it deserves a closer look at it. We also conducted follow-up interviews with students who attended the seminar series. So far, we interviewed 5 undergrad students, 2 first year and 3 senior. We asked them to do 3 to 5 Lean proofs from this list and talk to us about how they would go about doing a Lean proof and about tactics they choose to use. 1 out of 5 students installed Lean on her computer, and the other 4 students did the proofs on the Lean web editor. We haven't transcribed and analyzed the data yet. In the near future, we will be able to share what the data has to offer. Next steps. We plan to have a second round of the Lean seminar series, either repeating what we did for different students or having 2 intermediate sessions for students who already are familiar with the software. We would also like to continue to cooperating and communicating with the Lean community on Zulip, Zulip chat. It is a very friendly community, especially for beginners. In the chat, if I click on it, you should be able to see. This is Zulip, and you see the streams under all the stream. You can see there's a stream called Lean for Teaching. So this is a good place to post the questions or find people to talk to about the teaching. So the Fields Institute, today's meeting, I posted to there, and then people responded. Okay, let's go back. More importantly, we would like to collaborate with mathematicians who teach with Lean, hopefully starting in the fall, so that we can have a systematic evaluation of math courses taught with a Lean component. Please feel free to contact us if you're interested. We're happy to hear any comments and suggestions about the project. Thank you very much.
Thank you so much, Kitty and Gila. What a fantastic set of presentations today that took us from mathematicians' use through students' experiences. So just let's take a second and thank our speakers. Thank you so much. We now have about 30 minutes to engage in some Q&A with our, particularly our speakers from this afternoon, Paola and Athena, Heather, Gila, and Kitty. I'm happy to field questions for people who want to use the mic, or feel free also to put your questions right in the chat box. All participants should be able to unmute themselves. So Kevin, I see you've got a question raring to go.
So Kitty, why did you choose Lean?
Thank you, Kevin. Should I say something for Gila? Or Gila, would you like to answer that question? Gila? Okay,
yes. Well, when way back when I worked on a book on proof technology in mathematics research and teaching, I communicated with several people engaged in ITPs and ATPs. And at that time, I talked to Jeremy. Jeremy, you are there and you can hear. And he had moved from Isabel to Lean. So this is part of what convinced me to go with Lean.
I know very little about teaching with Isabel, but Isabel is somehow a simpler type theory. And I wonder whether one would see different results teaching with Isabel, because somehow in some technical sense it's less complex, but I don't know if that actually has any kind of pedagogical implications.
Well, thank you for the question.
On the topic of pedagogical implications, we did have a question earlier from Jeremy to Paola around why are Lean users better at using ordinary languages in their proofs. There was some back and forth in the chat box, but in case people didn't notice it, Paola and Athena, if you wanted to elaborate on your responses, this would be a great time.
Yeah, so what I was writing in the chat was students come to university never having really to worry about the way in which they write mathematics by and large. They also come with thinking that mathematics doesn't need words, and because you have mathematics symbols and all these things, which we don't know, we know that they aren't what is desirable. In fact, there is quite recently some research about what mathematicians like to see improved produced by students in terms of language and organization. And this research that comes out of Kirsten Lowe, PhD, who is in Texas. Where is Kirsten? Can't remember, in the US. It basically talks about an academic style for writing proofs that mathematicians worry about this, because in school they write something and it gets marked. The encounter with Lean makes them realize that actually it's important where you put your commas and your full stops and all this. So that may be the case why they then start using full sentences and a punctuation and kind of linking from kind of particles like in and so on, which we didn't really see very much in non-Lean user, even in proofs that were correct or were judged to be correct. So this is what we think. We think that Lean helps with the distinction of technical languages. So you have three languages at play here. You have mathematical languages, you have a computing language, and then you have the natural language with which we talk to each other. And we think that is the experience with Lean that helps with this, also because unlike, I think it was, somebody was saying this afternoon, unlike kind of writing a maths coursework and then giving it to somebody to mark, Lean tells you immediately, no, I really don't like this, there's a mistake here. So we think that this is the issue.
Can I also add something, Paola?
Yeah, sure.
So it was also very interesting to hear the students comparing the Lean proofs and the proofs that they're seeing in the lectures, or the proofs that they are writing themselves. And they talk about Lean as a person who accepts proofs. So Lean would get very angry if I wrote this, for example, are comments that students are making. And it's very interesting, speaking to a few more experienced users, they were saying that they They see the proofs shown in the lectures by their lecturers, and they would say, okay, this is a sketch of a proof. It's not really a proof. And there are quite a few aspects that are not very clear from how the logical steps are not very clear. So they had this distinction much more clarified compared to possibly their peers. Sorry, just wanted to add this one.
Thank you so much. I know Jeremy also had a comment that spoke about maybe shifting students' attention away from simply calculation images of math to this maybe more complete picture.
I think that's just consistent with what Paula said, that, you know, that the question is when students turn in an assignment, what's the content, right? And if the content is actually getting the commas in the right places, then, you know, then, I mean, it's really the substance is the argument.
The connection to like this personal identification is really quite neat. And I wonder what Lean would think about maybe our next question, try and segue. But Pamela has asked in the chat something that built from Kevin's question around how to minimize how overwhelming it can be to just choose a platform when there are so many. And as we're coordinating multiple languages, we're also coordinating a lot of understanding of the technology, the math pedagogy, and so on. I think that's an open question if anybody wants to tackle it.
So I'd like to, so in fact, I meant to respond to Kevin's original comment, and I started talking, and in fact, I had muted myself. So no, because I've also used Isabel for teaching, and it's also a great tool. One thing that's nice about Isabel is that it's really built around the kind of declarative proof language that Heather likes, you know, have this by blah, 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 have this by blah, blah, blah. And Isabel has a lot of automation. So it's, you know, have this by auto, have this by auto, you know, it's really the kind of style that ideally you want, you know, you want the students emphasizing the steps. And when something is just, you know, obviously followed from the things before, it should be okay to just say, you know, from the things that came before. I think, you know, I think at the level of teaching between Lean, Isabel, Cook, and so on, I think they'll all work. They're all fine. I think, you know, what we're going to need to make any of them really feasible or useful for teaching, it's really kind of the local tooling of, you know, doing the kinds of things that Heather wants. You know, the things that should be a one-step inference should be a one-step inference. One thing that's nice about Lean is that Lean 3 and the next version, Lean 4, is really good for customization. You know, if you want to build in, if you can figure out, you know, this one kind of inference that you want students just to be able to do in one step, you know, should be able to implement that in Lean. But yeah, I think I think that the tools are not really where we want them to be, you know, for using in the classroom, but they're getting there.
Thank you, Jeremy. For people who are monitoring the chat, there's also some discussion around introducing geometric components. I see Vivian might have a question, and Kitty, did you have a response to one of our questions that you'd like to share? Perhaps just before Vivian asks a new question.
Yeah, let Vivian ask questions first.
Yes, thank you. I have a question. First of all, I would like to thank everybody for the presentation, and the last presentation by Gila and Kitty. I have a question to you. You said, and I completely agree, that this ITP should not replace the other tool that we have for the teaching and learning of proof. And my question is, did you begin to design some activity where the students are free to use or not the ITP depending on what they think they need to do it? So to have it as something which is present in the situation, but not designed to be used. So I wonder if you already did this or if you plan to do this, and how do you see this? Thank you.
Thanks, Vivian, for the question. We're not there yet at this point. What we're thinking is to collaborate with mathematicians. Let's say the mathematician is teaching a intro to proof course, and we could maybe run a couple or several tutorials with a lean component, and then we build activities or teaching materials or exercise there. So that's the plan. And we do need support from lean experts. Like in the team, we have Yuri. We will need help from him to put together something that we could offer to students. Lean is free. You're free to install either 3 or 4, although 3 is recommended. So once we have the package, I know in France, Patrick developed a whole package for his students to use. So there's a lean environment. It's easy for our students to access. And there's a bunch of things he wants his students to do. I think that's the goal for us. We want to have something similar to that so we can offer to students. However, we want a course to have a lean component rather than just expose the software to students, because there's a lot for them to deal with on top of the mathematical content. So that's the plan. We're hoping this year we will make more progress on that. Gila, do you have anything to add?
Actually, Viviane, we will get back to you on that as soon as we know that we have lean taught at the university. We will plan on having special tasks, and we will certainly consult with you as well, Viviane, because you've been in that area for a very long time, and we want to continue the collaboration. So get set.
Okay, thank you. And in France, we have now a small group. And today there is Antoine Meyer, Julien Arbou, and Robertia, who are part of this group. And we have a group who is having a reflection on this ITP. And with different ones, we are in contact also with Patrick Massot and we Lean Eduquera, as it is written in the chat, and others. So yes, we are working and developing some reflection about this. So we will be happy to be in touch with you.
That's wonderful. Paola, you have something to add?
Yeah, I wanted to say, so I think that the important thing, if you want to go out and talk to students, is that Lean needs to be a compulsory part of the module, an assessed compulsory part of the module. We had these difficulties throughout all the studies we did with Asina. In none of the setting, Lean was compulsory, and it was just too difficult for the students to engage. So there was no motivation. There were the few really keen that went for it, and they're all now doing PhDs and so on. But if you want to have a little bit more of a broader thing, you need to go somewhere where this is part and parcel of instruction and of assessment, which is also what we're looking for, because we also don't have this yet.
And that does seem to be the trend with other sorts of educational technologies that are getting introduced in the classroom. I want to raise a message that was put in the chat just before we get to your next question, Kevin. This is from Eva. She would like to raise 1 or 2 more or less heretical, but of course not new thoughts. She's wondering if what is taught proving in Lean is more an artificial kind of mathematical knowledge or a kind of prothesis with regard to mathematical reasoning and proof. One possible test for that would be to investigate how far the students improve their abilities to do mathematical argumentation and proof in a conservative way. And she thinks the real benefit in mathematical practice is when it comes to really complex proofs. But in the educational context, the formal effort is quite high compared to what you can do with it and express with it here. So like Jeremy said, you might teach it just for the pleasure of doing so. More of your thoughts on that. I'm not sure exactly to whom it was directed or if it's a general question, but we can float it in the air for anyone who wants to tackle it. Jeremy.
Yeah, I mean, again, this goes back to exactly the question of that Kevin raised. You know, why are we teaching lean, and why are we teaching anything, right? I mean, these are the big open questions. I want to point out that, you know, the mathematical applications, that's, you know, the applications to learning ordinary mathematics aside, which are important. You know, I also want to emphasize that that the technology is now becoming increasingly important in computer science and industry and so on. I mean, the software is used to verify hardware, verified software. So, you know, if one of the things we want to give students is knowledge that they can then use to go get a job one day, you know, we're not hurting them, right? Learning to use formal tools. So that's, you know, that's one ancillary goal. Another one is, look, there is a hope in the community that, you know, that formal methods, automated reasoning tools, and so on, you know, can benefit mathematics. It's not just teaching mathematics, but can become part of mathematics, that, you know, that they can be used to help discover new mathematics and so on. So it's hard to distinguish between, you know, is lean helping students learn mathematics? Well, if lean and things like that are becoming part of mathematics, then that's part of the game. You know, next semester at Carnegie Mellon, I'm going to be teaching a course on formalization specifically. And the decision was, you know, first let students, you know, math majors come in, take the intro mathematics course and learn how to do mathematics. And then specifically teach them, okay, and now here's how you formalize. So not try to conflate, not try to pretend they're the same thing, and so on. So that's one choice you can make. You can say, look, there's ordinary mathematics, and then there's formalization, and let's not pretend that they're the same. But then the hope is, you know, I'm hoping that students will take it early on, because then later courses they take, you know, maybe they're just taking an ordinary abstract algebra course, but they do have this formal tool and this formal library. So yeah, I think they're interesting questions as to whether it's the medium or the message, or, you know, or where in the spectrum it lies.
Thank you, Jeremy. I like the idea of an ordinary abstract algebra course.
Yeah. Old-fashioned.
Even better.
Yeah. Kevin, go ahead.
I was going to just mention something. It was raised that lean was not a compulsory part of many of the courses which were being taught. And I've just this semester finished teaching a course where lean was absolutely compulsory. The first time I'd ever done so, an undergraduate course for final year students in mathematics. And it was entirely project based. I set no formal, I set a lot of puzzles for them to solve, and they got 0 credit, and I videoed myself solving them and put the results on YouTube, and there was 0 credit for any of those. And I assessed the entire module via 3 projects, and the first project was, you know, write a proof of a theorem you learnt during your first year at university, and then write a proof of a theorem you learnt during your second year, and then finally write a proof of a theorem you learnt this year. So sort of forcing them to become more adept with both the technology. But this is all within the context of mathematics, which they were already supposed to have known. Because this was the thing that I learned from Paola and Athena, was that if you teach people, you try and teach people equivalence relations at the same time as teaching them how to use a vastly complex piece of software, that's not going to go well for the majority of the students. So I was taking final year students who knew the math already, and this course was absolutely unashamedly, this was about trying to learn how to use the theorem prover. So somehow it did become clear after a while what the goals of my course were, and it really wasn't to teach them mathematics; it was to teach them, you know, how to tell mathematics to the computer. And it's been an absolutely fascinating course, and I will talk about it at Paola's conference in Loughborough in a couple of weeks' time. But these courses are there, and they will hopefully start appearing, courses where lean is a compulsory part of the system.
Thank you, Kevin. Paola, I see you have a response, and I'll also invite, if you want to share information about your conference in a couple of weeks, if there's an online component, we'd love.
we put the poster on in the chat, and there is a clickable link, and you can register to come online. Obviously, it would be great if you could come to Loughborough, but I understand if not. I wanted to say to Kevin, I know I'm aware of that module. Somehow there is a difference if you want to introduce Lean as one of the things the students see when they arrive at university. Then you are thinking about the contribution in terms of this transition, and you're thinking about, is this going to help the students understanding the rigor of mathematical language? Is this going to help them understanding what is mathematics or what we mean by mathematics and all this stuff? When you teach Lean in a fourth year or in the third year of the degree, you are focusing more on the actual difficulties of the software, where you have students that hopefully have sorted themselves out in terms of proof and writing and proof production and so on. Not to say that it's not interesting, because it is, and I'm really sorry that we missed the boat this year somehow. It was just too busy, and it would definitely be something that is worth looking at. But I was wondering whether it would just be possible to try to use this tool to also facilitate this transition, which is notoriously incredibly difficult in respect to kind of formalization and proof and all these things.
I found that some of the students were rather less good at proofs than I was initially expecting. Actually, that was one of the things I observed, was that the idea was that the first year maths was supposed to be easy, but then some of them were just saying to me, I just feel as stupid as I felt in first year all over again, which I thought was a wonderful comment, because it did make me start thinking, well, did you actually understand this material the first time around?
Maybe that speaks, Kevin, to doing that same course, but having them do it a little bit earlier in their, maybe in the second year in their careers.
There's a related question in the chat from Julian, who wrote, he's quite convinced, even if it still needs to be studied scientifically, that ITP is useful for teaching introduction to proof. But what about teaching maths more generally? Do you think it could be useful there as well?
I've been using it to teach myself research level mathematics, done by Fields medalists. And I suspect that's not really what the question was about. But I'm using it to organize my own thoughts, learning difficult new mathematics. But that's not the actual question. The question is, can we teach undergraduates using this tool, or is it something else?
Yeah,
I don't know the answer.
I'd like to say that I'm hoping the answer is yes. I think it would be great to have, an introduction to abstract algebra based on Lean, and an introduction to discrete mathematics based on Lean, and an introduction to topology or real analysis based on Lean. And I don't quite know how to do. I mean, I guess the ideal would be if, we have everybody come in and take a course, take an introduction to Lean, and then after that they can do all these other courses. I practically, I don't know how to get there, but it would be nice.
Gila, did you have a comment as well?
Yes, I think our experience in mathematics education says yes as well, because when we introduced the geometric sketchpad, when we introduced Cabri, when we introduced GeoGebra, it helped a lot in general in teaching mathematics. And we hadn't expected that, but this is what happened. So I believe there is no reason not to expect this to happen. When you introduce a new tool, you introduce new cognitive situations, and it can only be beneficial, as far as I can tell from our research experience in mathematics education.
Thank you, Gila. To add to that, I think we have seen in the talks today, there's a balance of teaching mathematics, but also teaching mathematical practices, proving approaches and ways of reasoning with mathematics that weren't always at the focus when students were going through the proofs that first time around, but maybe now have come into view a little bit differently. There was another comment from this time from Howard, who wants to add to some heresy. So why not? It seems that the greatest benefit from mastering proofs is not in mathematics, but rather in helping foster productive civil conversations on broader societal issues by creating an ability to investigate definitions, assumptions, and the validity of inferences from evidence. Do any of the platforms focus on these critical elements for arriving at consensus rather than on the strictly formal and limited mathematical logical applications?
So I can say something about that, which is, so the Lean has a communal mathematics library called MathLib. As I mentioned, it has more than 800,000 lines of formal proof in it now. It's maintained by a small group of maintainers, but it's open, anybody can contribute. And the procedure is people will write up a piece of mathematics. They then do a pull request. They say, I'd like to add this to the library. And then there's discussion. People will say, okay, was this? So ideally, before somebody does that, in fact, before they start work, they will actually come to the community and say, hey, I'm thinking of formalizing this, and there will be a discussion. So it does happen at that level. There are discussions of, how best to write definitions and how it will fit in with the library. And then when people do submit code, it's reviewed, and there's a lot of discussion. So there is a platform for, yeah, I mean, that's one aspect of that.
Just going to quickly pause here since we are at 1:15. So we are formally sort of at the end of our time. However, I don't want to pause the conversation for those who want to continue it. But for those who do need to step away, thank you so much for your participation today. And I know, Joyce, you might have a word to say before we formally close here.
Okay, yeah. So all I can say on behalf of the Fields Mathematics Education Forum, I would have liked to thank Kitty and Gila for organizing this fantastic forum. And I also like to thank all of the presenters. What a nice conversation. It feels like we need more. We need another forum to keep going and keep talking. So, but I also want to really especially welcome all the people that probably today was your first time in this Mathematics Education Forum. Now, just consider yourself, you are a member of this forum. So we would like to hear from you, and we would like to see you in a future forum for us as well. So thank you also for the participants, because the forum would not have happened if there were not people here to discuss. Thank you, everyone. We'll meet again at the end of April. We're working on an interesting topic. So thank you, everyone.
Thank you very much.